Please join me in welcoming the one, the only, the irreplaceable Casey Muratori.
Okay. Way too big. Sam made it way too big. I feel like before we start, we should also thank Sam for putting this together. It's been a very long time since I've been really excited to give a talk, and a lot of that is because the speaker list of this talk of this conference is absolutely amazing, and I don't know. I'm really excited to be here, and I'm excited to give this talk, so I'm just going to jump right into it. So I would like to talk about something that happened in 1998 at a company called Looking Glass, which normally, like back in the day, contemporaneous with this, if I had said Looking Glass, everyone would know who they were, because they were an incredibly influential game company that did a lot of firsts in gaming. One of their games, Ultimate Underworld, started kind of the 3D revolution in PC gaming, and they were incredibly innovative company at the time. And a lot of people today, I mean, there's people in the audience here who weren't even born then, right? So a lot of people today might not know who they were, but they were incredibly important. And one of their games was called Thief: The Dark Project. And it's a franchise that lived on. It was one of the first sort of stealth action games. And it looks pretty primitive by today's standards, obviously, but this was engine contemporaneous with things like Quake, for example. So this was sort of state of the art at the time. Now, I'm not going to talk about graphics, because I'm not qualified to talk about graphics anyway. I'm not a graphics guy. What I want to talk about instead is how they modeled entities. And normally, the way you would do things in games at this time, and in fact, the way that Ultimate Underworld 1 and 2, and then later System Shock was another one of their games, the way that they did things was actually the way that me and, for example, Ryan Fleury, who's going to be interviewing me after, we would say that this is a good way to do things even today. They were sort of fat structs, if you will. They just put everything in one structure, and when you were going to do things like have different types of entities, really all you had was some kind of a type field in there, or flags or things like that would let you know what you were supposed to do with it. But these were very, very limited resource times. I think the systems, you would expect to have something like 2 megabytes of memory or something total to run in. So you're talking about fixed blocks of small size, and everything has to work in that. So that's just what you did, because that's what worked. And in this time frame, right, during the 80s and then later 90s when this game was made, this is the sort of thing that was in vogue in the architecture world. This has nothing to do with how they were doing things at Looking Glass. This is what we would kind of think of as a normal OOP programming model now, where you have a hierarchy of things. Like there's an entity class, and then you have an NPC and item subclass derived from it, and then things below that and so on. And that was not something that Looking Glass had ever really used in that lineage of games in their RPGs. And they decided not to go that route, even though that was sort of what was in vogue at the time. That was what was you would have seen pushed if you were reading architecture things in Oops Law, or the kinds of papers that would have been published on software architecture. So they did something very different. What they did is said, look, we want all of our systems to be the primary thing that we're going to think about. We want to think about physics and combat and those sorts of things, the same things that were in our fatty structs. When we do a more serious architecture here, we're going to do more architectural work, we want to put things in terms of their system, not in terms of the entity. And so what they did is they came up with a system where they would use an ID, like if I have a particular object that I'm trying to model in the world, one of these entities, I just have an ID for it, and it doesn't really have any data associated with it at all. It's kind of the polar opposite of a fat struct. So they would just say, we're going to use the IDs to represent things, and then the way that we form the entity's data is we just use that ID to look up into a system and say, what's the physics like for this thing? What's the combat like for this thing? This fuel system I have, I'm just imagining systems you might have in a game. And in so doing, in 1998, when they shipped Thief, the Dark Project, they shipped, to the best of my knowledge, the first instance of an actually commercially released entity component system. That's what we call it today, right? People call it this. This is now an in vogue architecture in much the way that those hierarchy kinds of architectures were in vogue at the time, and still to some extent are in today, but not necessarily in the game industry. So this was the first time I'm ever aware of anyone shipping this kind of model. And in fact, it's the first time I'm aware of anyone even talking about this kind of model. I'd never heard of it before. This was the first time. And there is a pretty interesting thing that you have to understand about this, and I know this may seem like beating a bit of a dead horse here, but those red lines that I've drawn there are basically encapsulation boundaries. And this is a very important theme throughout this talk. I just want to really make sure I hammer it home. Encapsulation boundaries are really what we care about when we're doing architecture. What we care about is where we make it difficult to access things and where we make it easy, right? And so what they chose to do that was very different than that sort of inheritance hierarchy model is they chose to draw the encapsulation boundaries around the systems. Now, this is very different because the traditional OOP model, right, is you draw the encapsulation boundaries around the objects. So the encapsulation boundary in a normal OOP-like hierarchy is I have whatever the object is, like a mech, and the encapsulation boundary is around all of the things that the mech knows about. But that's very different than this. This is about all of the things that are related to a system, not all the things that are related to a mech. Now, it's important to remember, this is not like not OOP. You could easily call this object-oriented programming. It still obeys a lot of the principles you might recognize from object-oriented programming. So it's not like they were saying, we're getting rid of object-oriented programming. They were saying something very different. And they were saying, effectively, what Mark Blank said, he's the person who actually implemented a lot of the system. And what he said was, for some reason, OOP has gotten into this mindset of compile time hierarchies that match the domain model. Meaning, if you think about what you're trying to model in the real world, like entities and guards and things like this, or even if you're just thinking like the natural world, we're going to think about, birds, and are they, is it a mammal or is it an avian thing, right? You're thinking about this domain model that you're trying to model in the real world, and you're bringing it into the software world. And what he was basically saying is like, why are we pushing this? Why is that the idea, right? And he says we can still do OOP-style stuff, and we can just do it by changing our paradigm of what we're thinking about in terms of our domain model, right? Don't make the domain model be in the code. Make that be something the user experiences, but the code is done in a way that makes sense for the code. So this is really brilliant, and it's a great way to summarize it. It's one of my favorite crystallizations of that concept. So I would only add one thing to it, and that's that word encapsulation, because I think sometimes people think hierarchy, they just think the relationships. But it's the encapsulation that's really important, because that's what really determines whether or not the code is easy to write or hard to write. It's are those boundaries in the right place. So this is crucial. And this talk is kind of about mistakes, as you'll see. And I made a mistake one time. I went on this thing, you may have seen it, it's called the internet. It's like this series of tubes that connects people around the world, and it's kind of complicated, not 100% sure how it works, but they have a thing on it called social media where what you can do is there's like a box, and you can type anything you want into the box. It doesn't have to be correct, it doesn't have to be coherent, it certainly doesn't have to be polite. And then you have to push this button, there's usually a button next to it, but the button says different things sometimes. You push the button, and everyone in the world has to read it, like everybody. And that's an amazing invention. I was probably doing something like that at the time when I saw some people talking, having a discussion about this sort of thing, discussion in quotes, let's say. And they were thinking about this. They were thinking about, we have old things that were like maybe not quite architecture, like those fatty structs things. And at some point, people started saying, there's this other architecture we could do, which is this hierarchy thing, and that's like much cleaner. It's much better organized. It's better architecture. And they started to push this, right? And it definitely got adopted everywhere. And it's a very standard paradigm even to this day. And they were sort of responding to people who were saying this is bad, that this hierarchical thing is not a good idea. The encapsulation boundaries are in the wrong place, as I would say. And they're saying, okay, there's no way that all of these smart people who pushed this stuff and who created this, there's no way they could possibly be wrong about it, right? Like, surely this comes from all kinds of like academic studies and ways of looking at things, and we definitely have great examples of this working perfectly, I'm sure, and it all got translated to us, and you guys just don't understand, and we don't understand either because we're not really sure what we're saying, but we're basically saying that someone must have known, and those people were smart, so there you go, right? So could you really be saying, all you naysayers, that it doesn't make sense. It didn't come from a logical place. And so the short answer to that is absolutely that's what we're saying. That's 100% what we're saying. And the long answer to this is the rest of this talk. Welcome to the Better Software Conference, the inaugural Better Software Conference. This is the Big Oops, which is my sort of attempt to go back over 35 years of history to figure out where we went wrong. Like, how did this happen? Okay? Now, just get some things out of the way first. And this is mostly for the people. I don't know where I'm looking. Is there a camera out there? That. This is mostly for the people. The people in this room are probably already bought in, right? Low-level programming, that sort of thing. You're probably like, okay, I like where this is going. People on the internet, as I said before, maybe that was a mistake, but they're going to have some issues with this, some bones to pick. So I just want to say first, when I say the big oops, anatomy of a 35-year mistake, I'm not just talking about OOP as a whole. I'm talking about looking for very specific things in it, okay? And because whenever you talk about OOP, it's always this thing where people are like, well, whatever you're talking about, like, that's not really OOP. Like, you're talking about these things, you're using the terminology wrong, or that's not how I write code. It's like OOP is just a thing where it's like, it's how I like to write code. And whatever they're thinking at the time, that's what OOP is or something. And I don't necessarily blame them because it's a nebulous term and they have their own definition for it. I mean, I probably have my own definition for it. That's totally fair, right? But I just want to say we're not going to be dealing with any of that here, so I don't want to hear the whole, like, I don't know. It's sort of like wine, which I've got the slide up in here. It's like, if you have like a designated origin, you're not allowed to call it certain things, and it's that kind of feel, right? It's not actually OOP, it's sparkling code or something like this. You have to use the right term for it. So I just want to be clear, I'm talking about something very specific, and it's the thing that I just said. Very, very specific, and I'm not saying OOP was a mistake, I'm saying this was a mistake. The idea that you're going to draw encapsulation boundaries around these compile time hierarchies that are based off of whatever you're trying to write. Now, second thing we want to get clear is I don't want to hear any complaints that no one ever pushed this model, because I know that's going to happen. I'm looking at you, Y Combinator. I know that this is going to be a thread. So, anticipating that, let's just say we have a lot of historical evidence. When I was doing the research for this talk, I read so many things from the historical record. It is so obvious that everyone actually 100% meant you should look at the domain model and you should code that directly into compiled hierarchy. For example, here is literally Bjarne Stroustrup's paper, What is Object-Oriented Programming? To tell you what it is. And he starts off with the shape example that I've used before that everyone said, well, that's totally ridiculous. You're just cherry picking out of an introductory book. It's like, this is where he was trying to explain this and sell this to people in his industry who were experts. And he says, look, if we're going to write something like this that has kind k as an enumerant there of like what the kinds of shapes are, right? If we're going to write something like this, we end up with code that has a switch statement in it. So when we want to draw something, we have to say, oh, what is this? And I have to say, okay, case circle, case triangle, and have the different drawings for that. And he's like, this is a mess. You can never do something like that. Instead, what you want to do is make a hierarchy where it matches the domain model. I've got a shape class, and then he derives from it the triangle class, and there's a virtual function, and all those sorts of things. This is right in the first papers where people are selling this concept in certain programming languages, right? And I guess I should also point out that he says things like, when we're talking about object-oriented programming, literally what we're talking about is inheritance hierarchies with virtual function calls. Like, he says that. And he says object-oriented programming is programming using inheritance. So hammering home that this is literally what we are talking about. There's so much evidence, and I'm just picking one paper. Now, a lot of people will talk about, say, Alan Kay, because he was a big father of object-oriented programming. He's the one who coined the term, as far as anyone knows. And he talks about, this sort of idea that OOP only means like messaging and a few other things, right? He said this. And so some people might be like, well, that's what object-oriented programming was really about. No one was ever pushing it. And Bjarne Stroustrup, okay, whatever, C++ is terrible. Like, don't listen to that guy, right? Despite the fact that he made the language that's like one of the most prevalent. It's the one that we all use mostly, or at least have for the past 20 years. And so this is the truth. This is the actual truth here. It's like, yeah, he said that in 2003, right? He said that after a very long time. So why did he say it? It's because 10 years earlier, he was already saying he kind of soured on it. He's like, inheritance was like really powerful, but people just didn't know how to use it. Novices and experts apparently both couldn't use it, right? It was just, it's really good, but no one can figure out how to use it, I guess. So that's a little bit weird. I don't know. Maybe Alan Kay, he still comments on stuff. Maybe he'll come to tell us what he actually was trying to say there exactly. But if you go back earlier, because Smalltalk is a lot earlier than that, if you go back and look at what they were actually talking about when they were talking about Smalltalk, in the times before they had a chance to reflect and say that it didn't work, well, here's what they were saying. Inheritance programming shows the power of differential description, right? They're like, you can take an object, and I can say, like, I'm going to start with this completely undifferentiated object, and then I'm going to derive a rectangle. I'm going to drive. And in fact, here's a diagram from one of his articles talking about, like, cool things in computer architecture. He's like, we can have a generic object, and then we can derive from that a rectangle, and we'll derive a window, and a paned window, and a browser. Look, everyone is talking about literally representing in the hierarchy what your domain model is. That's what they're talking about. And if you need further proof, look at what's actually in Smalltalk. We have all the data, like for this, all of the papers exist. Here is an example from the art and science of Smalltalk where they're talking about some stuff that's needed to adapt values. Like I want to convert values between things and actually exchange values between objects and stuff like this. And here's just a hierarchy that they drew of stuff that they were using for implementation. That's the hierarchy, right? And if you look, it actually says, well, it's only part of the hierarchy for this thing, because like we couldn't fit it on the diagram. We had so many classes we were inheriting here, right? And guess what? If you liked the shape example that keeps coming up, that everyone says, well, no one would ever actually suggest that you use this sort of ridiculous shape example. You're just cherry picking, except it exists absolutely everywhere. It's in Smalltalk. There it is. They have a path class, and from that path class, they have different shapes derived from it. That's what the path looks like. That's in the base language of Smalltalk that Alan Kay and Robson shipped, and Adele Goldberg was the person who documented it. These are the original authors of Smalltalk, right? And if you don't want to take my word for all of that, you can take Bjarne's word for it. He criticizes Smalltalk for being all about inheritance. That's all it was, and you had to actually use it to get anything done in that language, right? And he's actually saying C++ at least doesn't make you do it that way. You only have to do it that way when you think it's a good idea, right? Which, by the way, I agree with him on that. That's why that's why I'm still able to use C++ to this day, is because Bjarne Stroustrup was actually really smart about a lot of things, and he didn't try to force you to do things only his way, whereas Smalltalk kind of did. All right, so now that we've got that out of the way, let's talk about the origin story for this guy right here, who has caused me so much pain and I won't even go into it. Anyway, let's talk about the origin story. So we'll start with C++, because obviously that's the most impactful language that really promulgated this inheritance hierarchy concept out to the world in a way that we all kind of experienced. Not only in programming C++, but obviously languages like Java, which are incredibly prevalent in not exactly our circles maybe, but obviously in business world and that sort of thing. So it's not even just C++. It's like the knock-on effects of C++ also. So this is really, really important as an entry into where this came from. So let's start in 1978 and looking at that. And Bjarne Stroustrup is actually in he's in university at this point. He hasn't actually gotten to Bell Laboratories where he would do the later work on C++. So he is working on his PhD thesis. And again, as I'm going through the historical record here, I really want to try and give you a mindset of what the people were thinking as far as I could get it from their writings, right? I went only through primary sources for this, and I tried to figure out what were these people feeling, like what were they doing when they were coding. And so he is actually working on distributed systems. He's not a languages guy. He's not there like researching languages or anything like that. He's working on distributed systems, and what he wants to know is, look, we've got some stuff where we want to know about hardware protection, like, if you kind of think of virtual memory or things like that, where you have hardware features that are designed to protect different parts of your program from other different parts of your program, or different processes from each other, or different nodes in a system, all those sorts of things. So he's doing distributed architecture work. And what he wants to do is run simulations, because at the time, again, putting you in the mindset of where we are in computer history, you don't just have computers lying around like we do today, right? It's not like, oh, I can just buy a bunch of computers and set up a network and do testing on it. It's like, no. There's no way he was going to get things like a distributed multiprocessor system to just play around on in 1978 unless he was extremely important and working for the military or something like that, right? So what he had to do was write a simulator. And what he decided to do to write the simulator, because earlier in his career, he'd been in university, I guess earlier in his education, I should say, he had been at university, and he learned from a person named Kristen Nygaard, who was actually one of the creators of Simula. He learned the language Simula directly from one of its authors, basically. Like he was actually there at the time when the author was also there, and this was how he knew what Simula was and how to use it. And so what he did was he wrote a simulator for distributed systems in Simula, which is kind of exactly what it's designed for, right? It's a simulation language. And he had a great time doing it. He was like, this was so much better than what I'm used to. I really liked the experience of writing that. So he ended up with this thing where he had like little programs that were simulating what was happening in a distributed network, or distributed system, I should say, not necessarily on a network. And he found that it was really easy to debug the little programs by themselves, and the language made it really easy to do that. Now, again, it's important to remember, keeping all this in your head if you can. I know it's a lot. It was a lot of reading, right? So I'm trying to convey it to you in as close as possible. Just pointing out, it's important to remember that that's the domain model he was working with, is lots of little programs that were talking to each other, right? So anyway, he says that the class concept that Simula had, because it had the same sort of idea of a class as C++ would later have, he said that that class concept that Simula had was really good for direct mapping, right? Remember I said compile time hierarchy that exactly models the domain, right? He said that was working really well when he was implementing it. He was just saying, oh, this is the thing I'm trying to simulate, and so I'm literally going to create classes in Simula that model that directly, and that was working really well for him in Simula. And you know, we can kind of start to see how this is breaking down. He happens to be working on something that is literally a domain model of things that are encapsulated. The computers can't talk to each other. The different processes in the computer can't talk to each other. It's an exact fit for what a class actually does. This is important to remember. Okay, so we used hierarchies for this, right? They weren't necessarily particularly deep, but they were the kind of thing where it's like, I have a computer, I derive different things from the computer, and those things are just kind of self-contained. And he had a really great time doing this. Again, he said very positive things about it. And one of the things that he really liked was the fact that the type system, when you had these hierarchies, that type system would catch errors for you. Exactly the kind of thing that we maybe take for granted today, because most languages, even JavaScript now has like TypeScript, right? Most things that we work with today have the ability for you to do this kind of type checking that catches a lot of errors at compile time. That was relatively new at the time. And I don't mean new in the terms of like no one had ever thought about it before, but I just mean a lot of languages you might be using at this time still had very weak type systems. And in fact, Strustrup complains directly when he's talking about this, that using Pascal kind of sucked, and he didn't really like it, because the type system didn't work very well for expressing things and for catching errors. He felt it was kind of more trouble than it was worth. So that forms his basis for this idea that classes are really good and type checking on classes is really good, right? And you know, just to split those down the middle, I do think the type checking part's pretty good. It's maybe the class part, or rather the hierarchy part, that I'm like a little bit suspicious of, right? But at least half of it I'm with him on already, even. Okay, so that's sort of what you will see if you read the Wikipedia or something, right? That's the simple part, and they often leave a lot of stuff out. So I thought, because this is a Better Software conference, I would include a much more interesting aspect of this story, because you would think, if you saw a thing that's like, hey, what happened was Bjarne Strustrup was doing stuff with distributed systems, and he wrote this thing in Simula, and it was a great time, and so what he decided to do when he got to Bell Labs was make C++, and it would just have, you know, the classes in it from Simula. It was great. No. So what actually happened was the entire thing completely rolled over and died. He tried to run the Simula program, and he had all sorts of problems with it. And it started even before he tried to run the Simula programs that he was writing. What actually happened is, first, he hit the same things we hit with C++ today. Build times were through the roof, and it was almost impossible to make changes to the program, so much so, and I'm going to let this sink in for a second because it's really awesome. So much so, I mean, I almost want you to read it. If you compiled 1/30th of the program and tried to link it, it was slower than just recompiling the entire thing. Okay? Let that sink in, because it means that Bjarne was talking about Unity builds in 1994. He was like, we can speed this up by not doing incremental. Incremental builds sucked that long ago. Anyway, but I digress. Anyway. The runtime also was lousy. He couldn't get the thing to run fast enough because Simula was extremely slow. Anyone want to guess why it's slow? It's a rhetorical question. I'm going to tell you why it's slow. It was slow because of the garbage collector. Same reason things are slow today half the time. The garbage collector was taking 80% of the runtime, apparently, even though there was no actual garbage that needed to be collected, because, I guess at that time garbage collection was even, very, very primitive, obviously, so it's probably running all the time just to see if there was any garbage, and it was like, yeah, nope, no garbage. And that was happening a lot, so 80% of the time. So he had the experience with Simula that we have with C++. Like, it is if the chain continues, right? The garbage collection, obviously not so much. So that's what happened. He had to rewrite the whole thing from scratch in a different language called BCPL, which has no type checking whatsoever. I mean, that's not entirely true. It has very, very minimal, but none of those class things and that sort of thing. So that's the actual story of what happened. So it's kind of interesting. It presages everything, right? The whole thing is almost like a microcosm. So if we reflect on this for a second, again, I think I've tried to highlight the important points there, but the other thing to remember is a lot of people talk about these things. They talk about those compile time hierarchies and all that sort of stuff, and they say, like, here's the thing that you just don't understand. It's all about large teams. It's all about these large teams. It's just that you got to have large teams, and if you had large teams, then you would understand the magic of the compile time hierarchy stuff and the encapsulation. It's amazing, right? How big was the team that Bjarne Stroustrup was working with when he figured this stuff out and thought it was good? 1. He's doing the same thing we're doing. So these ideas don't come from some kind of analysis of what we're going to do with lots of people. So you could argue maybe they turn out to be good for that. But you certainly can't argue that anyone was designing it for that, because they weren't. They were doing it for themselves. Stroustrup was doing it for the protection, the type protection, the error checking, that sort of thing. He wasn't doing it and also like the virtual function kind of stuff. He wasn't doing it for large teams because everyone at Cambridge University was helping out in the project. No, he was a lone wolf coder. He really was. So anyway, goes to Bell Labs. He makes C with classes, which is the first thing that it's the original name of C++, called C with classes, because that's what it's going to be. It's going to be taking Simula's type system and putting something like that into C. And the reason for that's pretty obvious. He goes to Bell Labs, and C would be like a lingua franca there, probably, right? Because they're the people who make Unix. They're the people who make C, like the people who are at Bell Labs, the people making these technologies. So he is tasked, when he gets to Bell Labs, with doing the same sorts of distributed systems analysis that he was trying to do at Cambridge. He's trying to do those things for Unix. He wants to analyze certain behaviors of it and that sort of thing. And he finds the same exact things. He would like to write in something like Simula. He doesn't want to have the same disaster that he had where he had to rewrite everything BCPL. So he's like, could I take C, add classes to it, and get the best of both worlds? Something that actually runs and doesn't fall over, right? But that has some of these features that I've been enjoying. And so that's what he's doing, and he's doing it for the same reason, right? That sort of modularity and concurrency analysis kind of stuff. He's trying to figure out how these things work and run simulations of them. Same exact thing is happening, and it's happening over again. And what he kind of complains about with C, if you didn't have these things, some of it's a little confusing. Like, he talks about the fact that he says all program parts can poke into all of the memory, and C++ doesn't really change that. But I think he's just kind of talking about private declarations, right? He's just like, well, obviously I don't think you can stop programs from poking into the memory by putting private on it, but it will stop programmers from typing it into the compiler, and that's sort of the same thing, right? And where that comes from, this sort of idea that we're going to protect things, that actually comes, again, from his distributed systems sort of OS thinking background. Because he's looking at hardware, and he's looking at things like virtual memory and protection that you get between processes and those sorts of things. And he's saying, that's kind of what I want for programming. I don't really want to make those mistakes where I access the private part of things. I want to be able to wall those off. And he's thinking about actual hardware, computer hardware. That's where that idea comes from. Again, it doesn't even come from working on large teams or anything like that. It comes from thinking this might be a nice feature, just like the computer stops it, right, from happening, the compiler could stop it from happening. And that's where const comes from too. It comes from an OS metaphor. He's thinking about whether or not files have write permissions to them, right? Are they read-only or are they writable? That's what const is to him. That's where he thinks about it first. So again, all these things come from a very different place than what you would think if you didn't go back and read the historical documents. And by the way, these aren't hard to find. These just come from the D&E, which is a very popular book that he wrote that's just a collection of his papers, right? So a lot of this stuff in the first part of the talk, you don't have to dig that hard for. All right. So anyway, we get to sort of a second wrinkle at this point. And what happens when he starts using this stuff is it's important to, I shouldn't really say what starts happening. Let's say one of the things he does is he uses the inheritance that he puts into this sort of C with classes, because he's just going to do the same thing that was happening in Simula. He uses that inheritance in a way that would generally be frowned upon even by him today. And that is to do things like implement a linked list and reuse it. So what he does is he says, OK, I'm going to take a block that's like the linking part of things, and I'm just going to inherit stuff from it so that all the things that inherit from it can go in a list, right? Now, he would never say to do that today. He would say use a template or something like that, like a parameterized type, right? But it's important to remember at that time, this was a thought. And this thought actually does come from Simula as well. We'll get to that later. So it's important to say, in addition to the modeling part, they're using inheritance for the purpose of code reuse, even if it really doesn't have much to do with anything. That's sort of an adjunct split. And I just want to include it here so that you understand all of the things that were being thought about with inheritance at the time when it was actually being put into more mainstream languages. So that's what he was, one of the things he was doing with it, in addition to the domain modeling part, which is more of a direct mapping. OK. And you can see him here criticizing it just to hammer this home. He doesn't think you should do that anymore, and he said as much in parameterized types for C++, which is where he started to talk about templates. As soon as he sort of got his answer to how we were going to do these sort of things, as soon as he got like a parameterized type model, because that wasn't new to C++, there were languages like Ada and Clue and stuff that had that in there, he started to say, OK, C++ has never had a good way to do this because you had to do the inheritance thing. That's not fabulous. Parameterized types are the way to go. So he knows that too. It just takes a while to get there. Right? OK. So that's kind of the end of it. And virtual functions come in a little bit later. The first version of C with classes, when he's first starting on it, doesn't actually have virtual functions. He eventually does put virtual functions in. And when he does, this is what he says about it. He says it was borrowed from Simula and presented in a form that was intended to make it simple and efficient. So he was thinking primarily about, I want something kind of like what Simula has for this ability to call functions without knowing the type on them. But I want to make sure it's very fast, because that was a concern that he always had, again, because of the disaster he had experienced directly with Simula. So again, reflecting on this, it's totally different from what you would think if you just read like the capsule summary. Like, he's not talking about large teams still. He's talking about literally, we're just working on this thing. I'm using inheritance for some reuse of code, and I'm using it to directly model the compile time. At a compile time, I'm using it to directly model the actual domain that I'm working in, which happens to be distributed systems analysis yet again. So we have to jump at this point, because that's pretty much all we can get out of C++. I mean, you kind of got the picture now. Everything else is like after the fact. Everything else is post hoc. Anything else about C++ was people making stuff up after that, or adding things to it after that. But that's where it comes from. So if we want to actually know where these ideas started from, we've got to go back to Simula. We've got to say, well, OK, if all this stuff came from Simula and him using Simula, well, where did it come from in Simula? Like, did they just make it up? And Simula originally comes from something called the Norwegian Computing Center. I mean, we are here very close to Norway, I suppose. So some of you may have known this place. I didn't really know anything about it until I read that, was reading up on Simula and like, OK, there's this place. It's a quasi kind of private public institute for doing computing research. And it's in Oslo, Norway. And in 1962, these saucy gentlemen right here, and I'm apologizing, like, Sweden is the worst place to give this talk, because now I have to pronounce their names in front of people who probably know Norwegian pronunciation very well, and so I'm going to butcher it, and I apologize. It's Ole Johan Dahl, maybe I can pronounce that correctly, and Kristen Nygaard. And you already know Kristen Nygaard's name because this is the person who Bjarne Strustrup learned the Simula from originally. He interacted with him a lot when he was at his previous university before Cambridge. So these are the folks who make Simula. They're the people who actually are kind of like the masterminds behind it. And the first reference we have to it is in private correspondence that has now been published from Nygaard to another person who was working on operations research. And these folks, operations research, if you don't know what that is, it's when you look at how systems are behaving in order to optimize them, basically. So you can think about things like we're trying to plan how the military is going to organize some things, like what is their process going to be, and we want to maximize the throughput of like how we're manufacturing this thing, or how we're going to load planes onto an aircraft carrier. I mean, I don't know anything like that, but a lot of it's military because that's where the funding comes from. But it's for anything really. It's also in business, operations research, things like the simplex algorithm. If you ever heard of that, that's operations research, et cetera, et cetera. So anyway, he says, like, I got this idea. What I'm going to do is I'm going to make this language that makes it very easy to describe one of these systems. And then what I will do is use it to describe these problems in a way that allows it to do the simulations automatically. So it's like almost like a scripting language for system simulation. And if you look, this is some code you can find when they talk about the history of it. This is in 1963, the Simula language would have looked like this. It's one of the earliest snippets I could find. And so this is not the way the final Simula looked. This is sort of how they started out. And you can see what it essentially is, and you don't need to understand exactly what's going on in this for the talk, so I'll spare you the details. But essentially what you're doing is you're setting up these various things like customers and stations. It's like things, we're imagining like entities moving between parts of a system, and we write little pieces of code that's like how they will be processed when they get there. Like, will this person, they'll be held for a little bit of time, and then we'll check to see if they've paid the fee, and if they've paid the fee, we'll send them to this station. If they haven't paid the fee, we'll send them to this other one. And the idea is you just describe that system this way. You run the simulation, and it presents you with a bunch of statistics. So you can kind of see, like, okay, this is where the bottlenecks were, or things like that, And that was very successful. They eventually released a thing called Simula 1, which was the first sort of more widespread version of this thing. People loved this. They could do their system analysis this way. But Nygaard and Dahl were thinking in their head, like, we really like this thing, and we think it has possibility to be bigger than what it is. It's going to be like more powerful than just what we had in that first version. So they start to make a new version, which eventually goes on to be called Simula 67. And this is like, it's like Windows 95, right? At this point in time, people are starting to name languages where you append the year of the language after the language. So we have things like Algol having that, or COBOL 60 is the version of COBOL that was first introduced in 1960, right? And so that's what Simula 67 would eventually be. And they're trying to figure out what they're going to do for this new version. And what happens is they're thinking about code reuse. They're like, we don't really like how we have to rewrite things a lot of times, and we're trying to figure out some way that we could get some of this reuse in there. Like, we want to reuse these things, and it's not really working out very well for us. They're looking for a solution to this, and they're not really finding one. But eventually, when they're thinking about this problem, they're saying, what if we have like a bridge with a toll booth on it, and we've got cars going across it, and they might be either trucks or buses? What could we do so that we could just write this once and have it work for both the trucks and the buses, so we don't have to like duplicate all the stuff we said for trucks and buses? That's what they're thinking of. And this is not me saying this is them saying this is what they were thinking. This is what they were trying to solve. Literally, this is what they were trying to solve when they came up with classes. And here is what those classes look like. You can see up at the top there, it's defining link class car. The link is a thing where they have this linked list sort of superclass that they're deriving from, and they're going to have a car. Then they're going to say underneath cars, they're going to derive a car class truck and a car class bus. There's different kinds. You can see load and capacity are like two different data members that those have, okay? So in this one snippet, we can see both things that not only they are about to do, but that Bjarne Stroustrup is about to do as well. We are using this for reuse. We are deriving from a link class to get its functionality, not because we think that we are like a link in the domain model. But then mostly what we're doing is following the domain model with our classes. It is car, and underneath it, it is truck and bus, exactly like would eventually be promulgated as how to design OOPS systems with those hierarchies that I was talking about. So that's what it looked like. And they literally said, hey, this now allows us to quickly just say, this thing's a link, and then it can go in lists. Awesome. Now, you'll notice they didn't actually talk at this time very much when they were counting the history, and I guess I shouldn't say you'll notice. I noticed because I had to read the whole thing. They don't really talk about the virtual function part at the outset, right? They're kind of talking about just this reuse part. That's mostly what they're concerned about. But they do eventually care about that virtual part, because once they do this subclassing, they're like, we want to have ways that the subclasses can do things in addition to what the parent's doing. And that's where the idea from virtual functions comes from. They say, we have these operations that we were defining, things like what that queuing behavior was going to be that I showed on the original slide from Simula back in 1963. And they're like, we want to have those operations be modified based on whether this car is a truck or a bus and things like that. So that's what happens. Now, if you look at how this had to actually work, it works the same way that primitive code reuse works. If you wanted to use it today, if you want to use inheritance for things like links, it worked exactly the same way. They literally had the sort of class hierarchies. Like you can see in the middle there, class simset and simset class simulation. That's basically saying, like, look, all of this stuff is going to be derived from like linked list holder. That's what SimSys would be like. Like, I'm a person who holds linked lists, and then we're going to derive the simulation from the thing that holds linked lists. That way, it can use that. So it's almost like a library. Like, they're using inheritance like a library here, as well as the domain model, which is under it. So again, that same double duty. All right. So again, just to hammer it home, nothing about teams. Nothing about architecture, none of this stuff, right? It's all about trying to solve a code reuse problem, and then something falls out of that. No analysis is done of any of the things that you would normally say if you were trying to promote the use of domain modeling via those class hierarchies, right? That's not what's happening. So, this is where we actually got compile-time hierarchies of encapsulation that match the domain model. Because Simula actually did have encapsulation. You couldn't refer to things outside of the entities like that very much. And so it kind of did have the beginning of that. It wasn't as rigid as C++, as we'll see, but that's effectively what it was. So I don't know how to summarize all of that we just saw. Basically what I'd say is, effectively, what we sort of were seeing is this came out of sort of an approach to templates that wasn't very good. Like, that's sort of what happened. And it's not their fault, because, I mean, they're in the wilderness, right? Like, nobody knows any of this stuff. We take for granted all the things we know today. They don't know any of this. They have to invent everything. But that's really what they almost wanted. If you had handed them templates at the time that they were trying to do this, they may never have invented this class concept at all, because they just wanted a linked list. They just wanted a way to say, I have lists of things going across, right, or whatever. So that's sort of where they had started. And they just happened to come up with a virtual function thing, which, by the way, is useful for stuff. I'm not trying to suggest that it isn't. But that was sort of a byproduct of what they were trying to do, which was just make a list class they could reuse, kind of. All right. So that's the end. That's the entire story. Now you know where everything came from. I mean, of course, if you only want to do sort of the capsule version, that's, you know, again, sort of the Wikipedia version of it. But you have to kind of ask the question, I mean, we know that they did those things, but, like, where did they get the idea for those things? I mean, that's usually how I approach things anyway, right? I'm like, after I find out that, like, someone got the idea from someone, I'm like, well, do we know if that guy got the idea from someone? Because I want to know about following it the whole way back, right? So that's the end. If you just use a capsule Wikipedia summary again, you'd kind of get something like that out of it. What you probably wouldn't get is this stuff. So when you actually go digging in here and you pay attention to every little thing, and every time you come across something that someone mentions, you're like, wait, what? And then you go try to pull the papers that they're actually referencing. You start to find out a lot of other stuff. So if we keep pulling this thread, what we find is the idea of subclassing is not credited to Nygaard and Dahl. They credit it to somebody else. C.A.R. Hoare, actually, the guy who invented quicksort. That's who they say this idea of subclassing came from. They don't claim to have invented it. They claim to have invented a version of it that was derived, pun intended, from Hoare's work, right? And this is the paper that they're referring to. This is the paper that I believe they would have read, although I'm not sure exactly which version they read, because different versions were circulated, and there's actually sort of a further comments one that happens after this, but they would probably be aware of all of this, because academics are always very good, right, at sharing their information this way, putting out publications. I mean, it's the thing that is cred for them, right? Like, your papers are your cred. So you're reading papers by other people, you're writing your papers. So they read this paper for sure. Which version exactly, I couldn't tell you. But this is the paper, and here's what Hoare is talking about in this paper. He says, all right, we have, in the real world, and I want to underline that because it's like compile time hierarchy that matches the domain model, right? In the real world, we have objects that we want to model, and they have different versions of things, and we want to model that sort of discrimination that's happening there in the subclasses. And so he gives the example of an algebraic expression. He's like, if we look at an algebraic expression, I'm trying to model that. I want to represent that in the computer. I might say I have an algebraic expression, and then I have these different things that are types of algebraic expressions, right? And he says constants, variables, dyadic expressions, right? He's trying to model language. And by the way, this happens a lot. I don't really cover it much in this talk because it's not relevant, but you'll see a lot of people this time were working on things like how do we parse stuff, right? So they're thinking about how do we parse language, how do we parse computer languages, how do we parse human languages. So they're thinking about this kind of thing all the time. It's like, what if I want to represent an equation? How am I going to do it, right? And he's saying, what about these subclasses? And he would literally write it just like this. So as we can see, Nygaard and Dahl were not lying. They 100% did get this idea from that. It looks almost exactly like theirs, down to the syntax. You can see that he's saying, I'm going to have an expression. Here are the subclasses of the expression. It's going to be constant and variable, right? And so this is what Nygaard and Dahl read, and they were like, oh, wait a second. What if we just had like our cars and trucks and buses under them, and then we could just use the car, and then we put the car across the bridge? Okay, that would work. Wait, but we don't have to stop at the car. We could make something above the car that's like things that are in a list of stuff, and then we could use it for everything. It doesn't even have to be the bridge. Holy cow, dude. Like, thank you. Thank you, Tony. So anyway, yeah, Anthony, they call him Tony Hoare. I think that was, he didn't go by Anthony. Anyway, sorry, thing I didn't introduce ahead of time. It's just up here because I've been reading this stuff for, I don't know, months at this point. Anyway, so when he presented this in this paper, it doesn't stop there. And this I found so interesting. And we're starting to get into stuff now where like I had never heard before. A lot of this stuff, when I digged into it, I was like, how come everyone doesn't know this? Because it's super cool. When he presented this paper, or I shouldn't say presented this paper, when he wrote this paper, he included discriminated unions in it. Tagged unions, whatever you want to call them. If there's FP people out there in the audience, they're going to scream at me for using the wrong term. But you know what I'm talking about, something that has a type in it and then subclasses inside it, and you don't know which one you have until you look at the type. And then you can use whichever part makes sense for that type. And this is a super powerful programming idiom. I use it all the time, and I think it's one of the best programming tools you have for things like dynamic polymorphism. I absolutely love it. It's in this paper in 1966, right? A long, long time ago. And this is his way better than anything I get to use today in C++ thing he suggested for what you would do when you wanted to use one of these. He said it's a switch statement, which of course wouldn't be called a switch statement at that time, but it's basically a switch statement that says, I want to use this object, and I'm going to tell you what each type, whatever the subtypes might be, I'm going to give you a different block of code to run depending on which one they were, right? Again, functional programming, I believe, would really like something like this, right? It's doing that discriminated union thing. And furthermore, he gets the fact that this adds type safety and prevents errors. He gets the fact that the code that would come after the then statements can now safely refer to the subtypes because you've checked what the type actually was. And he says that right in the paper. So he totally got it. He knew way better than any of the knock-on languages, I guess from C++ on. He knew way better even at that time how cool discriminated unions would be if you had the right language constructs to work with them in a type-safe way. So I thought that was super duper awesome. Now, if you think about it, if this was in the paper, and Simula read the paper, and that's how they created Simula, or the class concept in Simula and the idea of subclass Simula, and then C++ came out of Simula, well, why don't we have, why wasn't this a first order feature? Where did the discriminated union part go? And the answer is, well, Nygaard and Dahl actually put it in. It was called inspect. So Simula actually had this. You didn't have to use virtual functions. Simula was way better about that. When Strustrup went to do his classes, he took it out. He thought that discriminated unions were bad because they broke modularity, right? It's because now someone from the outside can tell what class you are. So we lost out on one of what I consider would be one of the most important features I would use in C++ every day because it got removed when Simula was playing telephone with C++. All right. So there you go. That's where the concept actually comes from, right? It's this paper by, Anthony Hoare. He's Sir now, by the way. He's been knighted, I believe, right? And again, not a single part of it. There's no hint at all that any of this is really about compile time hierarchy stuff or about large teams or about any of the things we talked about today. It was literally like, hey, I might have a record that wants to have a type field, and it would be cool if I could just switch on the type field and do different things based on it. How about that, right? And that's what I would have wanted. So we had that already back when this paper circulated in 1966. So really the whole string is about us getting a really bad version of discriminated unions. We had them already, and now we don't have them. To this day, I don't even know a standard variant really works as well as this thing would have, right? And we could have had it from day one if someone had just believed that this was good. All right, so that's the actual end. We've gotten back to kind of the point of the first part of the talk. There's another half because it goes way further back than that, but I want to give everyone a chance to kind of stretch out. So I don't know, can we take a break? Where is Sam? Can we take a break for a few minutes?
Yes. How long do you want?
I don't care. I can keep going if you don't want, but I figured, yeah, I can stretch.
Let's go to 25.
Okay. I'll see everyone back here whenever that is, at 25. Okay, so as you saw in the first part, you come to the end a lot of times, but then it's like, well, is it really the end? You keep digging. Turns out you didn't really get to the actual meat of, the origin story. You didn't really get to the part where, I don't know, I'm bad with comic books, but Bruce Wayne and the falling pearls and the Joker and that kind of stuff. Like, we actually gotten back to that scene, and that's the scene that everyone wants to see in the movie. It's like, how did he become Batman? So what we're going to do here in the second half, I promise there's only this one more half. There's two halves. I'm not going to psych you out again. What we're going to do here is we're going looking for Batman, right? So we left off, we've got this paper on record handling by Hoare, right? Famous for Quicksort, like I said, one of the fathers of computer science. And the interesting thing is, and this was really hard to figure out, but I was trying to, where did he get the idea? Did he come up with the idea? Was he sitting around? What was he working on, right? And it was really hard to find this. I wish that I could find a document where he talks about it. If any of you out there ever find a document, because, I did the most research that I could do in the time that I had to figure out where these things came from, but I'm sure I missed something somewhere. So if anyone can actually figure this out, I would love to see it. But after a lot of digging, I figured out something pretty interesting, which was that actually there was this committee that was supposed to update ALGOL. Now, ALGOL was a programming language that was very popular at the time. It was in use since the early 60s, actually. Actually, it might have even been before that. I don't remember because it's not that relevant to this particular timeline. But what they were going to do is, much like Simula had an update from Simula 1 to Simula 67, here there's going to be an update of ALGOL up to this new version that would eventually be called ALGOL 68. And the people who were working on this, it's like a who's who of computer science fame, right? So Hoare is on this, and so are a lot of other people like Nicholas Wirth and that kind of people, the person who invented Pascal or created Pascal, right? So on this committee, there was another guy, and his name was Douglas T. Ross. And this is a name that I had never seen mentioned ever before. I have no idea who this guy is. And I'm like, wait, what? And, oops, sorry. And when it was talking about it, it was like, oh, in some private correspondence, because Alan Blackwell and Kerry Rodden, not really a part of the story, but they're like, we talked to Hoare privately about where he got those ideas, and he said that they actually, a lot of them came from this guy named Ross, who he had conversations with when they were on the committee. And I'm like, okay, so what's this about? And Ross had this thing he called a plex, which is a record-like data structure, and apparently this was something that really influenced Hoare's record-handling paper, which would eventually go on to create the rest of the chain that we just went through. So that's one thing. And another thing is if you look at the other branch, the branch that I'm not really covering very much in this talk, because again, we don't program in Smalltalk these days, right? The closest thing you would get is maybe something like Objective-C. If there's some still people out there using Objective-C, you know, like Apple was using that for a little while. So Objective-C kind of came from a Smalltalk background as well. So, but it's another huge branch of object-oriented programming. Smalltalk was very important. It's influential, at least in the research or in the understanding of OOP, right? It was a very pure OOP language. It pushed OOP a lot further than a lot of the other languages by saying everything is going to be object-oriented and that sort of thing. And of course, it invented the term object-oriented, so everything's going to be like Smalltalk, which is what object-oriented was, right? If you look at what Alan Kay talks about for his inspirations, like where did he get his ideas from Smalltalk? He lists some things, and there's some like the Burroughs B5000 and this file system from an Air Force base that had to do mostly with dispatches. We could go into that in the Q&A if anyone cares. But one of the things he talks about is Simula, which we've already covered, and the other thing is Sketchpad. He talks about Sketchpad all the time. This was a huge, hugely impactful thing for Alan Kay. And Sketchpad was like this drawing program, right? I was aware of Sketchpad. I mean, maybe some of you are aware of Sketchpad. It's pretty famous. You can look up demos of it on YouTube, for example. So we've got this Ross guy that I want to look into more. I'm like, what's going on? And then we've got this Sketchpad thing, and I'm like, I think I remember Sketchpad, but I don't really know why that would have inspired Alan Kay to do object-oriented programming. So I'm going to look into this more. I want to see, just make sure I've got the whole story before I really say the end like I fake did in part 1. So let's go back even further. 1952 now. There's this place called the Servo Mechanisms Laboratory at MIT, which is kind of an amazing name. I would love to be able to tell people that I worked at a servo mechanisms laboratory. But this fellow right here, that is Douglas Ross, who now I know exactly who he is and what he did. He goes there, and he's first on the job in 1952. He gets to this laboratory. And what their sort of whole mission was, this was Department of Defense, United States Department of Defense research stuff. What they were trying to do is build a system where someone from the Air Force could describe a part that they were going to try to manufacture, and the computer would just make it. It's almost like the birth of 3D printing. And they actually did demos of this. They had stuff working where you could type in a description of an ashtray in the sort of pseudo language that they had that was meant to be kind of more, it's sort of, almost like in a Grace Hopper sense, right? Like something that's sort of, we're trying to get closer to human language, but it's really not human language because they don't have the ability to parse that yet, right? I mean, until large language models, we didn't have the ability to parse that, right? So when you look at something like this, what they're trying to do is say pseudo language, and our automated milling system produces this object out of it, right? And they actually have working, it's not entirely thorough, they've got it working, they have instances of objects you can actually look at that they made. So they're accomplishing this as well, and you have to remember how early this is. 1978 is, I date these by when the person's talking about it. This is the 1950s that they're doing it, right? So they're working on this simulation stuff, this processing stuff, and this where they're trying to take language and turn it into sort of CAD, right? The birth of CAD. And just to show you how early this is in the thinking about what's going on in computing, COBOL is generally again, in the kind of low-effort Wikipedia search version, COBOL would be the first thing you'd see referenced as having things like record-like structs, right? We all take a struct for granted. We're a struct is the simplest possible thing, right? It doesn't have inheritance, or it doesn't have virtual function calls or any of that stuff. We would just say, if we're just talking about a bare struct, a basic vanilla struct, that doesn't really exist. No one's thought about that, really. They have sort of an idea of data records that comes more from data processing, in the old IBM sense of the term. So they do have an idea of more of the database version of I've got some fields that comprise a record. But people aren't really thinking when I program, the computer program is also going to be written in terms of records that it's using purely for computation, not to store a particular piece of data on magnetic tape or something like this, right? But it's just purely an artifact of the implementation of this program. I've defined other records. They're not thinking about that. And even in 1960, when this was printed, this first version of COBOL, even in that 1960 time frame, this COBOL didn't really have that. all of its record stuff was pretty much still about data on tape kinds of things. It was in memory as well when you had a mirror of one, but it wasn't, no one was thinking really about that as far as I could tell. They're just thinking of it as storing data. Now, pedants will say that Plankalkül has this, but it was a purely theoretical language, just written down on paper. It was an early German programming language. It's very forward-thinking, so I don't want to disparage it at all, but it doesn't count if you just sort of wrote down, well, maybe we'll have this way to like put multiple things. It's like, no matter how rigorously defined on paper, you don't get credit unless you've actually got this working and you're actually programming, making programs in it that you run, right? So really, it's kind of not there at the time. So what people are actually thinking about is this, right? Lisp is gaining some traction here because it's developed over the course of the 1950s as well. It gets published officially in 1960 in this paper by John McCarthy, who obviously was one of the, I believe he's sort of the person who designed Lisp, and actually a different person at MIT actually implemented it, but that has nothing to do with any of this. Point being, he's obviously the father of Lisp because he's the one who had the idea, and he's the one that designed it. And he's starting to talk about Lisp and saying, this is a way that we could do symbolic computation. Now, remember, Lisp doesn't really have any concept of records at this point or anything like that. It's just sequential bags of stuff. So it's like, OK, we're going to have like a list of symbols, and to the extent that you're ever going to do processing on something that's like a record, it's just up to you to kind of remember that the symbols will go in a particular order, and that's how you're doing your processing. So they haven't really gotten this idea yet of structured data, like this is what the computer's going to process. They're thinking in terms of processing lists, right? Because, again, there's like no high-level languages. We got like Fortran coming in this time. We got Lisp coming this time, and then these experimental languages, stuff like that. We don't have all these languages that we know about today. So Douglas T. Ross, he's also working on stuff like this. They have a programming language that they're working on for this, computer-aided modeling stuff that they're doing, and he's actually thinking, what if we did structured data? Like, what if we were computing on things that actually had a fixed size? And this is all throughout the 1950s, they're developing this. And in 1960, contemporaneous with that Lisp paper, he publishes a paper. And in this paper, he keeps it classy. Right out of the gate, he basically throws shade at Lisp. He's like, look, Lisp is kind of dumb. Why would we compute only on things that basically have a next and previous pointer, or like a tree where it just has a left and a right? What would give you the idea that the things you want to compute on only consist of two things? What you're doing is you're just using that, and then you're constantly building up these like structures of like two-pointer things to represent bigger things. Why don't we just store the bigger things directly? And he knows why. He gets it. He says, look, not only does it take more space, but it also takes more processing power, because we've got to reconstruct the data we actually want by plowing through these lists all the time. And furthermore, we have to store them by keeping all of that interstitial stuff in there. And that's no good either, right? So he is 100% on point, and this is published in 1960, contemporaneous with the Lisp publication, contemporaneous with something like Algol 60. So way, way ahead of the curve here, right? Because that means they had it running throughout the 1950s. Now, he calls this a plex. He doesn't call it a structure. He calls it a plex because I'm guessing he's bad at self-promotion. He never gets this term to stick anywhere, so we don't type plex in front of our thing. But to be completely honest, as far as I can tell from history, we should. It should be called a plex. We should pound define plex to be struct, because that's where the credit actually goes to. It's this guy right here and the other people that were on that team. So what does it look like? This is one of the great things about this era. Everyone publishes everything. It's really nice. And it has to be condensed down into a paper because there's no YouTube, so I don't have to watch hours and hours and hours of things to find out what the heck is going on. This is an example of a complicated plex. This is in the original paper in 1960. And what does it have in it? Well, it has some data, an x and y coordinate, for example, right? It's just things that you might store like you would normally data members. It also has pointers already, right? These are basically things that are linking it to other things. So we've got data members, we've got linkage members, and hold on to your butts, because what is this stuff down here, right? Like, what is that? And I'm loving this, by the way, when I find this stuff in papers, right? Because I don't like to just read the abstract. I want to read the whole paper. Like, I paid my money, and I want to see the whole movie to the end. Even with the end credits, even if the movie sucks, I kind of want to know. I'm just curious right now. So I'm looking at this, I'm like, what the heck is that? TRA 562? Like, the secret code stuff going on. So what these actually are, and this is awesome, is check and fast are basically flags. And what Ross says is, look, when we're processing this stuff, think of it this way. We could run one subroutine, and just based on what we stick in the plex, we could change how we're processing it. So if we do want this thing to go through a particular path, we set it, and if we don't want it to go through a particular path, we don't set it, right? Just pausing for effect on that one. What's TRA 562? What's TRA 467? Those are addresses. That's an instruction. It's saying what we're going to do there is jump to a subroutine. Those are function pointers. So he basically says sometimes we don't really want parameterization of what's going to happen. We just want a completely different thing to happen. And there is where you basically have your virtual function staring you right in the face, right there in 1960, contemporaneous with Lisp. So I'll just say, our team, yeah, I was clapping for him too. Ryan, Team Fat Struct, we started in 1960, right here. We're like the old sort of thing at a university, like the old sort of the club, right? That's been going forever. We got roots, man. We got roots. We got hardcore stuff on our side. All right. So he throws up an example. He's like, hey, let's suppose we want to model a line, because remember, he's working on CAD. He wants to be able to type in, this is the shape of the airplane engine, and out comes the engine. So we're trying to think about things, how do we model lines, how do we model surfaces, that sort of thing. He's like, well, one thing we could do is we could take the data for the line, and we could put it in there. So those are like names of things, and X and Y coordinates things for like points. And then we could have like connected up with pointers, so a line would have a pointer to two different points, and the points would point back to the line, and we'd make basically a winged edge data structure, right? I mean, these guys were off the charts with what they were doing. It's kind of crazy, but doesn't stop there. So that is at the Servo Mechanisms Lab, which later gets renamed to like Electrical Systems or something. It's a lab that's still around today, I believe, but it has a slightly different name. I think it might have said it was even one of the longest running labs. Anyway, so hardcore. But there's another MIT, it's sort of like, it's not on the main campus in Cambridge. It's off in Lexington. It's called the Lincoln Laboratory, also very prominent. And this is the other side of a story. Remember I said we have this thing where CAR Horace saying, I got these ideas from Ross. He was pretty cool. And then we also have that Alan K part where he's talking about, hey, Sketchpad. So we haven't talked about Sketchpad. We found out about Ross, and he was hardcore. What about Sketchpad? How hardcore is that? Well, this is Ivan Sutherland. He's the guy who made Sketchpad, largely by himself. Like, he pretty much wrote it, again, lone wolf style. And he comes to the Lincoln Laboratory in the summer of 1960 as an intern originally. But he ends up doing his PhD at MIT here. So this is what he's doing. And in the course, there's these computers called the TX series. There's like TX0 and TX2. And they're basically made by this guy named Wes Clark. This is at MIT, and they're making the computers, right? I mean, that's the way this stuff worked back then. It's like the university actually had to make computers that they would use because nobody knows like what a computer even is yet, and they're like building different versions of them and figuring out what the heck's going on. And this TX series of computers, they were pretty unusual because they actually had a display. Like, we're back in the 1950s, right? So the idea that a computer was going to draw a picture for you that wasn't on a plotter that would like draw on a piece of paper is like completely unheard of. Like, no one's doing anything like that. It's very rare. And so there's only a few places in the world that even have a computer that can display something. But the TX series of computers can. And this guy who was architecting them, that Wes Clark guy, He was very forward-thinking as well, and he was basically saying, I think there's something here. I'm going to make it so it can integrate with a light pen that can see what's on the CRT, and I'm going to have the CRT be able to display stuff that the computer has. So he makes this new computer called the TX2, which is an iteration of TX0. There's no TX1, I'm told. I don't know the story behind that. But he makes a thing called the TX2, and obviously when you make something like this, it's hard to get time on it, because there's this one that was built. But he makes this, and it's under a thing for the Air Force, the US Air Force, where they don't really care what you do with this computer. They were funding it not because they wanted MIT to compute something for them, but because they wanted MIT to figure out what happened with large arrays of transistors for computing. Like if we make big computers, what happens? So this is very helpful because it means that the computing time on the computer isn't necessarily being taken up by some specific grant thing that they have to do. It's more flexible. So Ivan Sutherland manages to convince Wes Clark that he's got this idea for being able to draw on the surface of the thing, make a drawing program. Could he have a slot on the TX2? And thank God Wes Clark said yes. Because from then on, Sutherland went in at 4 in the morning, because that was the slot that was open, to work on this thing. That's the TX2, and that right there is actually Sketchpad running. And so he would work on this, and I mean, when I say work on this, you'll notice it's not like a keyboard here. You're not typing in code into an editor. It was still had to be manually entered in various ways, right? There was actually a secretary who would enter some of it. He entered some of it, right? So it's very laborious to develop things in the 1950s. Again, just to kind of hammer that home, these guys did not have much to work with. But he's working on this Sketchpad program, and what you could do with it is stuff that we completely take for granted today, as stuff you could just do. You could do things like draw lines with the light pen, just like we would with a mouse. And it's actually fairly intelligent. It knows things like snapping. Like if you go and you're going to connect back to a point, it knows that. It's not stupid, right? So it's not just doing random line drawing, it's thinking about those lines as well. We'll talk a little bit more about that because there's a lot more to cover there. But Alan Kay, who I said was the person who got us into this in the first place, the reason we're looking into it, he calls Sketchpad, the eventual thesis that Ivan Sutherland would publish on it, he calls it the most significant single thesis ever done. He says that it was so impactful and so important, not just to him, but to everybody. And honestly, he's probably right. Out of Sketchpad comes a lot of research in computer graphics. It comes the whole object-oriented concept from Alan Kay. The whole idea of interacting with a computer in this way is very, very new. CAD, and the idea of a CAD program kind of comes out of this as well. Now, it's so early in computing, I just want to hammer home one more time the kinds of things that Sutherland talks about if you read about his experience with Sketchpad developing at the time when he published the thesis. No one's ever even thought about, if I want to draw a line and then change where it is, I don't have to erase the line anymore. I could just move where it is. This is a completely new concept that no one's ever thought about before, because for the rest of history, if you drew a line, you had to at least remove that line before you drew it again, right? So they're literally figuring out here in real time the kinds of paradigms that we just take completely for granted when you sit down to use a computer. The fact that you can move things around by pointing at them, completely new. That's what we're talking about here. Another example of that is rubber banding. They were thinking, oh, when you draw a line, you must have to move the light pen along the line to draw the line, just like you would with a T-square or something like that, right? And they were like, wait a minute. We could just have the light pen attach the end of the line and move it around until you got it where you want it, and then you could let go, and that would be where it was. So even basic stuff like this was news to them. They were discovering it, right? So it's really, really early. That's how early we're talking about. Now, as fate would have it, when he's working on this program, who walks in but Mr. Douglas Ross? They were at separate laboratories, but they did talk to each other a lot. And the reason for that was because Ross's group is working on CAD. They're not displaying much about it, right? They're not working it interactively, but they're trying to do these machined creations that are based on human input. So because Sutherland's pretty new to this stuff, he talks to Ross and he's like, how do I make stuff like lines? Like, how do I do that kind of data modeling in the computer? Do you guys have ideas? And Douglas Ross is like, have I got an idea for you? It's called a Plex, right? And as we saw, Plex is pretty awesome. And Ivan Sutherland is probably one of the smartest people on planet Earth, so he recognizes right away this is a good idea too. So he's like, all right, we're doing it, right? He says, what I'm going to be making this program to do is have a bunch of like primitives, right? Like I've got lines and things like that I'm going to create. And I don't have that many types of things. Like I'm just going to have like lines, and later, actually, it was Claude Shannon, the father of information theory, right, who says you should put circles in it too. So there's all these kind of like little answers. If you actually go read this yourself, you'll find there's so many things I couldn't fit in this lecture because it would have been like 8 hours, right? But anyway, so he's saying we're going to have all these instances of things, lots of lines and stuff like that. So I don't really need anything more than just this end component thing, and I'll just have lots of those, and that's how we'll do it. This is how I'm going to write the program. And here's his diagram from his thesis about how he's going to structure, right, how he did structure lines and points, right? And there's some information missing from this because, I mean, if you're sketching things in Sketchpad with that light pen and it's very slow, right? He can't make slides with software like we have today. Not that the software I used to make the slides was particularly better than Sketchpad, but you get the idea. So it's not completely documented in here, but you can see here it's got the line, it's got a pointer to each of the points and so on, and the coordinates. He's sort of sketching that out. And hey, it's exactly like that paper from Doug Ross, right? And Doug Ross published this in 1960, so Ross and his team were already thinking along these lines before Sutherland even got to the lab, right? And started working on Sketchpad in the later, a little bit later in the early 60s. So that's how this whole thing ties together. Ross and Sutherland are like having a huge party here, and it's awesome. And if you remember, we had these things in the Plex that were basically like jumps, right? They were like subroutines. They were the virtual functions of time, or we maybe would call them not necessarily virtual functions, although you could implement that way. We just call them function pointers, right? And you can do all the same things you can do with a function pointer. That was something that Doug Ross was talking about in his Plexes in the original paper, and it's right there in Sketchpad as well. This is how he did things like, I want to go ahead and draw this shape, but I don't want to bother having actual different data types be completely specialized, having the routines completely specialized. So what I'll do is I'll just have like a few entries in the data type that say, how will I display it? What would I jump to display it, to figure out how big it was, or to move it. So again, virtual functions right there. They come from the Plexes. He puts it in, and that is how he actually implemented that kind of like parametric behavior in this program, in Sketchpad. Now, because we've already got one applause line before for this kind of thing, I'll just point out there's empty space in between these things here. And on the previous one, I was like, well, the reason that there's empty space on those is because we probably didn't have time to draw it out. And that was true for that diagram, because I know more about the data structure because I've spent way too much time looking at this program. But in this one, those are actually space in the struct. Those fields there's gaps, right? So why are there gaps? Why were there gaps in this thing? And I wanted to know, so I'm coming through this, just like, what are the gaps about, right? Is it just the same as the other one where it was like you just didn't draw it in there or something? What are the gaps about? I found it. At present, all generic blocks still carry space for all the information in any of them simply because of historical reasons. This accounts for the spaces seen in figure 3.7. What this means is Sketchpad is on Team Fat Struct, right? In 1963, he was still doing the same thing that the Plex was doing. He was just saying, look, maybe I should have gone back and tried to figure out some way to compact these, but you know what? We didn't end up doing that. And so he kind of just has that mention there. It's like, yep, all of them are the same size, and we just leave those fields out if they weren't going to be there, right? So I'm bending it a little bit there because in the Sketchpad paper, it's very hard to tell exactly the way, because he doesn't give explicit data layouts for a lot of things. It's hard to tell whether or not he was using like things that always had fat struct, or whether it was more like semi-discriminated unions, so there were pairs of things that would have been used differently. So it's either team fat struct or team overlay fat struct, but it's one of the other. All right, so we've come to the part where we can build our tree. As far as I can tell, it doesn't go any deeper than this. This is where it actually started for reals this time. Doug Ross and his team, this idea of Plexes. It goes to Ivan Sutherland because he works there, and he asks us for their advice on how to build the stuff in Sketchpad, and he picks up the Plex concept. It also goes to CAR Horror. That Plex concept goes to him because they sit on the Algol committee together. So that's our first branch. We then have that horror paper was read by Dahl and Nygaard, who decide to use it to create their Simula class idea. And both of those, Simula and Sketchpad, influence Alan Kay to create the Smalltalk branch of OOP. Meanwhile, the experience with Simula influences Bjorn Strustrup to create C with classes and then C++. Now, by the way, this is an inheritance hierarchy that matches the domain model. But there's a fun part of it. Some of you may know this, some of you may not, because, I mean, why would you? Obviously, we know C++ has multiple inheritance. It got multiple inheritance, not right away, but it got it eventually. Smalltalk never did. Single inheritance. However, single inheritance will get you C++, but it won't get you Smalltalk. You need two parents, right? What can I say? So that's the actual end. Now we've built our tree. We're finally done. We know where this stuff came from. Whew. Right? It was long. Of course, there is a personal angle to this as well, so I should probably say that the reason I decided to go do all this, it probably wouldn't be, I'm on that thing called the internet all the time. And most of the time, I'm just going to post something snide as a reply and not think about it again. So why did I actually go and do all this research just for this? Why didn't I just say, who cares about these things? I don't use those compile time hierarchies and just post something mean on Twitter. Why didn't I do that this time? It would have saved me a lot of time. Of course, I wouldn't have had anything to present today, but it would have saved me a lot of time. Well, here's why. Back in 1997, which, by the way, is right around the same time that we started this talk, right? The Looking Glass stuff that they did with Entity Component Systems was 1998, which means they would have been working on it in 1997. It would have been up and running at that time, so it's right at the same time. I'm working with a fellow called Chris Hecker, and I'm brand new. Like, I'm literally out of high school, so I don't know anything. Like, I programmed a ton as a kid, but if you ask me, my thoughts on computer architecture or something like that, I obviously would have answered very confidently and been completely wrong about everything. So he says, we're going to need a level editor. This is basically a game that we're working on. We need a level editor that does CSG on spheres. So the idea was you'd take these spheres and you'd build a level up out of unioning them together, right? Like a standard CSG modeling kind of stuff. But of course, I don't really know any CSG stuff. I really know how to do that. So I go using, I think it was Sightseer at the time. Like nowadays, you might use like Google Scholar or something to search for papers. So I go to use like Sightseer, I think was up at the time, or maybe there was a precursor to it, and I can't remember the actual one, but there were things at the time, even then, this early, because the internet's, the internet's only been available to the public for a short time, really. Like it was ARPANET, until the mid-90s, right? So when we're looking at this, I go to crawl papers and I'm like, okay, CSG on spheres, like to try to type some things in, read some papers, what am I going to do? And I come across this thing called alpha shapes. And alpha shapes are just the name that someone in a paper had given to something that was basically implicit services. I don't really know why they called it alpha shapes because it escapes me now. I'm sure I knew at the time because I had just read the paper, but for some reason they're talking about these alpha shapes. And I looked at them and was like, oh, it's like spheres, but when you move them together, they make this like nice smooth join. They don't make that hard edge. I was thinking, oh, for levels, that would be like really cool. That might be like way better than if we did CSG on spheres because it would have this like really cool effect. So it was kind of be like on the inside of these things, which are typically called metaballs, and it was going to be like sort of the negative space of the metaballs. So I made a modeler for this, and I called it Negaman, which has nothing to do with Mega Man, completely legally distinct from that. It's kind of changed one letter, and maybe it's the same, but nothing to do with this. It's just negative space metaballs, and this is what it looked like. And effectively, what you did is you picked things in it. You can see those spheres there are metaballs. They're the kind of spheres you put together, and they form these kind of surfaces. And we're seeing the inside of what you're creating, right? Because it's a negative space. So that's why it looks kind of weird. You would normally see the outside in a metaball modeler. but this is what I was working on. Well, and it's finished. Like, you can use it. I still have it to this day. You can model stuff around. It's pretty janky, but it does what it's supposed to do, right? And so the way that you interacted with it is you like picked those spheres and you could move them around by dragging the mouse and that sort of stuff. The same sort of things, right, that like Sketchpad was doing, only, you know, with much better hardware and much more advantages in terms of development. Same kind of idea because, you know, Sutherland was so far ahead, right? And so if you wanted to create stuff, you might select things like here. I don't know if you can see it. I've selected those two metaballs at the top, and then I've just like, there's a thing you could like rapidly stamp them down. I kind of just drag them and like stamp, 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 and you can create more of the level, just kind of like blobbing things together. So it was a selection-based UI, like most programs are, where I select a bunch of things, and I wanted the program to basically have a nice architecture for being able to do that, and then present the user with the user interface that would be appropriate for that selection. And this is actually a really hard architecture problem if you're not experienced, which I wasn't. Because it's like, well, if what you've been told is that you make these hierarchies, like these class hierarchies and things like that, and what we're really saying is, I'm going to select all these things that are really derived types of things. But now I want this higher level thinking thing to look across everything that you've selected and come up with a plan for what the unified interaction would be across those things. And then when you actually want to do the interaction, it's got to make sense for what's going on. And this is really tricky because the inheritance hierarchy thing doesn't help you at all for this. It fights you. You're constantly like, oh, do I just add a bunch of like functions to the base class that's anything you might want to do to a class? Do you basically fatty structure interface, right, but leave the hierarchy in place? There's all these things you might think to do, and they just don't work very well. But I was, you know, pretty gung-ho at the time. You know, I'm not old like I am now. So at the time, I don't mind typing a lot. So I go to town on this. I'm like, all right, I'm going to try to figure out how to do this cleanly, quote unquote, and we end up with crap like this. Now, a lot of times I try to convince people. I'm like, look, everyone thinks that I was like some C-only programmer. I just don't know anything about like huge, crazy, hairy, object-oriented programming or anything like that. It's just like, you don't understand. It's like, no, dude, I wrote some of the most ridiculous OOP stuff you have ever seen when I was like 20. I was doing crap like this all the time. It was awful. I'm not proud of it, but here is what's going on, right? So the way I chose to solve this problem, never mind the fact that like I'm doing the implementation inheritance thing up there with a template on the class. If you've ever seen this trick, it's an old school. So it's like there's so much stuff in this code base. It's a nightmare. But anyway, so if you look at what's going on here, I have get and set functions like you're supposed to have on any proper object. And you can get the center, you can set the center, that sort of thing, get the surface radius, set the surface radius, right? And now what I want to do is I want to have some way that these can be interacted with in a unified way. So what do? Anytime you create one of these things, I build a parallel structure. I create a property list that basically is callbacks using, this is called a rich hickey functor. I'm not kidding. It was a callback that you could use to do type-safe callbacks back in the early days of C++. I'm trying to tell you, where's the camera? Seriously, like I have done ridiculous OOP stuff. But if you don't believe me after seeing this, I do not know what to tell you. We can post more of this code if we need to. So anyway, so basically when it's created, it creates a parallel hierarchy that's just, it's not actually the properties, it's just callbacks that would get and set the properties, right? And then, you know, this is what that class looked like, right? Here's the get and set callbacks abstracted into a property. And then, if you wanted to use it, you could loop over the properties. You could create a modification that was typed on the property, right, to do the changes you actually wanted to do. Okay. And that's to support like dragging and undo and things like that. So this is what it looked like if you drew it out. I have a metaball with a radius and center. The data's in the metaball, right? Just like a good object-oriented programming thing would tell you to do. It's encapsulated inside the metaball. I create parallel, I call them property universes. I create property universes, all of the center properties, all of the radius properties, and they are callbacks to modify or retrieve the data in the actual entity here, right? The metaball. And then when you interact with it, you use modifications to interact. And this way, when I wrote the code, I could think about things in terms of the center or in terms of the radius. So what I do is when you multi-selected, I'd go, what are all the property types that you've had? And I'll just make interactions that work with those property types. And I'll put up little UI elements that work with those property types. If the diagram looks familiar to you, it's because you have a good memory, because this talk is very long. If I had a brain, I would have realized you don't need that. Just put the properties in the actual universes themselves and use an ID for lookup, and it's an entity component system. It's the same architecture, it's just I sucked at it and Looking Glass was good. That's the difference, right? So anyway, this was a slide I showed at the beginning. This is the slide that I did. You see what I'm talking about, right? My bad, right? This was my bad. I screwed up. I say that I don't blame myself because I was a kid, but really, I mean, I should have thought it through. So anyway, in 2024, when I was accidentally on the internet like I should not have been, I'm thinking to myself, how the heck did Sketchpad do this anyway? Because they must have had like the same problems that I had, because he could do all this stuff. It wasn't just a shape drawing program. I withheld some information from you if you've never seen Sketchpad before. I apologize, it's for dramatic effect. It's worth it, trust me. It could do a lot of other stuff than just draw. The just drawing stuff is the stuff that like Adobe copied or things like that, because that was the part that they could understand. The hardcore stuff, only Sutherland knows how to do. And here's what that looks like. You could say I want these lines to be like perpendicular to each other, and it would do it, right? You could take a drawing like this and pick a point that's not even a point. It's the intersection of two lines, and not just snap, but say, I want this radius from now on to always have its center point, like the circle arc, it's going to be drawn around that intersection. And not for snapping, but for always. So that if I then go do some constraints on this thing, which Sutherland's about to do, he's going to say, make that perpendicular to that, perpendicular to that, perpendicular to that, which you can't do in anything from Adobe, right? You have to go get AutoCAD or something for this. And by the way, AutoCAD didn't add it till like 2007 or something like this. They didn't have it in AutoCAD for like, right? When you tell it those things, you say, okay, that's what I want my shape to be, it'll just solve it for you. And if you move it, move the points around, it'll solve it again into whatever the closest shape is, right? Using like a relaxation least squares kind of thing. And I'm like, what the heck? I remember this, because I'd seen this demo before, and I'm sitting there thinking, you know, that whole compile time hierarchy thing in Alan Case, like he saw Sketchpad, and so I'd known those parts, you know, all the details I had to learn for this talk. But like, I'm like, what the heck did he do? He's working on this like crap computer. I get that he's way smarter than me, so fair enough. But he still had to do something, right? So what did he do? What does a really smart person do when they're faced with this situation? Because he's creating stuff that people who came after him, who have like crazy debuggers and WYSIWYG editing and the ability to run things quickly and iterate, they don't have to go in at 4 in the morning and enter things manually into a computer. How did he do it? Because no one did it afterwards for decades. So let's take a look. If we go in and we look at how he represented constraints, he represented constraints by saying there's going to be variables that are constrained. So I'm going to have some variables, things like this point or this line, that sort of thing, would be considered a variable in the system, something that is like a very primitive element of the system. So it could do that. You'd pick those. And then you would have a certain type of the constraint, essentially, which is like, what am I actually going to be doing with this particular constraint? But they're relatively generic in this way. And then the things you could constrain, scalars, points, instances, text, digits, and dummies. These are the different things you could constrain. They're sort of all like, again, sort of almost team fat struct there, right? They're kind of like all things you can reference as a variable without needing to know which one you're looking at. And so you can remember when we were talking about here's how those lines and points are. The line would not necessarily be something that was constrained, right? Because it's kind of it's a bigger thing than these are. But the points would potentially be something that was constrained, right? So you might say things about them in that way. And I don't know all the specifics of how the constraints work because he doesn't publish, like in the thesis, it only talks about it to a limited degree. So I can't give you a perfect breakdown of exactly every piece of the system, but I mined as much out of it as I could. And he goes on to talk about how this thing was architected so that he could solve things. He said, the ring structure, which we have not looked at yet, was designed to permit rapid constraint satisfaction. So what is this ring structure? What does he mean by that? But he's pinning it on that. He's like saying the ring structure was really important, and that's what's letting us do this stuff. He also says, all references made to a particular end component element or block are collected together by a string of pointers which originates within that block, which is kind of a type of ring structure, right? And he says this, which really throws you for a loop when you're first reading this thesis, in the data storage structure, the separation of general and specific is accomplished by collecting all things of one type together as chickens, which belong to a generic hen. Now, I will save you the trouble, those of you who want to read this thesis, about what those mean. A hen is a sentinel of a linked list. A chicken is a link in a linked list that points back to the sentinel, essentially, right? So, here is how the data is laid out. Type is a chicken, link, quote unquote. Spec B is a hen. So now when we go back to this type that we've already looked at, we can see them up there at the top. Type is the chicken, spec B is the hen. This is sort of the workhorse of the structural elements of the system. And the way that it works is that chicken at the top links it into a giant linked list with all of its siblings at its level of whatever it's doing. And the spec B hen is the sentinel for the list of all the things that are like subordinate to this thing. So it's like an up and down kind of a thing that's going on there, right? So chicken and hen. Here is how he actually draws it. You can see it's just a linked list, exactly like we expect. Key or hen threw me for a long time until I got it. Key or hen just means hen. For some reason, in the paper, he never says what a key is until this one part where he's like, sometimes I also call a hen a key. So anyway, okay. He then goes on to present this.
Humans have long
and
practiced
this is the
delegating work
runtime
that strains
structure
and tires them to
of
machines. It is their best achievement.
You start with a
Simple
universe,
counting and short-term
and it
memory are
has
often among
a
such challenges,
sentinel,
which the conveyor
hen,
throughput
right?
monitor
It
is
has a sentinel
specialized
that has a
in.
ring inside of
Simply
which
add
is
it to
variables,
any
holders,
belt,
constraints,
and
and
it will
topos.
tell you its throughput
Again,
after
not a
only 1
compile time
minute.
hierarchy, actually a runtime set of rings, right? So this is not baked into the compilation of this program in any particular way. It's just how the rings are structured at runtime when they are built. There are variables, holders, constraints, and topos. The ones we care about in this case, we don't really care about the holders much for understanding, but the topos are lines, circles, and pictures. Pictures are just like copies of things, like copies of other drawings, right? So the topos are the things that we're actually sort of the users interacting with at a higher level. The variables sometimes, like they see points and things like that, or text things they can edit. The topos are made up of those variables, right? A line is made up of points. And then the constraints are things that you apply to them. Now, it's important to notice, this is sort of, you could say, the opposite of encapsulation. What this structure implies is that at any time, any part of the system can go looking at anything. It's almost like a complete introspection system for what's going on. A topo, for example, that is a line, is not encapsulated at all. The 2 points that make it up are just floating in the breeze over there that you can go just grab, right? And you can do whatever you want to those points without that thing even knowing that it happened, right? So it's almost like the most unencapsulated thing that you could possibly imagine, which is probably why it was so cool. But if we draw it, oops, well, it kind of looks like this, right? The topos, you have a circle, it's got a radius and a center. It has pointers out to those actual things, which we call variables. Those are the scalars, those are the points. And if we have something like constraints that's going to operate on them, it just points into those things. And all of these pointers are typically like bidirectional. Like that ring structure is allowing you to walk in both directions if you want to, right? But this is the way that you're actually like conceptualizing the link in those cases. Once again, the same diagram, more or less, than what I had to write, which is the same diagram, more or less, than an entity component system is, because you are able to iterate over all of the properties you want to work with, which lets you implement things like a constraint, or in my case, a modification, right? In this generic way that operates on the pieces of things, or components in entity component system language, in a way that doesn't require this sort of weird abstraction thought where you're trying to figure out how to get things out of something in order to work on them. That was in 1963. So, to a first approximation, Ivan Sutherland was at the same level of closeness to an entity component system in 1963 as I was in 1997. And then people from there didn't notice. That's the only thing I can figure out. I have not found anything except for one quote that I'll show you that explains why the heck no one realized how important this was. They didn't think about the fact that the power of this system is coming from the fact that you can look at these components of things and architect around that instead of architecting around the bag, which who cares? Again, still object-oriented in its thinking. You don't have to claim it's not OOP. It can still be OOP. It's just where are the those encapsulation boundaries? Where are the boundaries, right? Instead of looking at it and going, oh, the important place to put the boundary was around this, that's where the power is coming from, they're looking over here. They're like, the power of this system was that. The ability to have virtual functions on it, right? The ability to say, if I want to draw this a different way, I change the subroutine. Now, I'm not trying to say that isn't useful. Function pointers are good in certain circumstances. But what inevitably happens is they're only going to get you the simple stuff. The only reason that even worked for Sutherland in the display case is because his display was simple. He didn't have to do things like intersecting stuff for hidden line removal or doing some kind of calling on it or who knows what. So he could just have an abstract display function because it never interacted with any other part of the system. It's the least interesting part of this architecture. Yes, it's cool. It's Doug T. Ross's idea about plexes. It's where it comes from, right? And that was a great idea, and we should keep it, but it's not the cool part of Sketchpad at all, right? It's the most trivial part of it. So that is the 35-year mistake. Oops, right? We had the answer. We could have been so far ahead if we just studied that and figured that out. Because it's so much more powerful to think about systems that way, especially the hardest kinds of systems like editors. This is the quote I was talking about. So, you can see here, this is Alan Kay, father of Smalltalk. And this quote breaks my heart, because I like Alan Kay. I think everyone likes Alan Kay. Probably, I don't know, maybe not. There's probably someone out there who hates Alan Kay. Alan Kay is very forth. He was trying all kinds of cool things. Xerox PARC is awesome. I'm not going to say something negative about Alan Kay. I'm just not going to do it. This quote breaks my heart because what he says in this quote is basically that the constraint solver, which he obviously knew about, because I happen to know that Alan Kay read the thesis. That's documented. Alan Kay says he read the thesis. And he paid attention to the constraint solver part. And he paid attention to it enough to know that what he called it omniscient. He was calling it omniscient, right? This idea that it could look at the properties like that and work on them, and Kay thinks it's a bad thing, right? He says, hey, there's this thing called Alan Barney's ThingLab, which is another program that was made later, a first attempt to go beyond Sketchpad, and he devised a nice approach for dealing with constraints that didn't require the solver to be omniscient. The omniscient part was the good part, right? That was the thing that was so powerful. It's why it's kind of torturous to make things in Smalltalk. I have dabbled in it a little bit. It's like, no, the encapsulation needs to be in the right place. You don't want to think of everything as these small little objects. So why did they? Why was Alan Kay so focused on that stuff? Why was Strustrup so focused on that stuff? And honestly, from reading it, oops, didn't mean to advance there or to go back there. From reading it, this is my best guess. Their backgrounds predisposed them not to want this, right? You look at where they come from. Strucev comes from distributed systems. Alan Kay had a degree in molecular biology. They're both thinking of little tiny cells that communicate back and forth, but which do not reach across into each other's domain to do different things. And so they're certain, Alan Kay especially, that that is the future of how we will engineer things. They're going to be like microorganisms, where they're little things that we instance, right? And they just talk to each other. So everything will be built that way from the ground up. But the problem with that is it doesn't seem to work in practice. It's a great idea when thinking about systems that are actually separated in that way, like actual computers talking over a network. It makes perfect sense because they do look like microorganisms. And most of Alan Kay's ideas actually map very well to things like the internet writ large, where you really do have to just pass messages back and forth. So again, not going to say something negative about Alan Kay. The ideas are good, and they do have very good applications. It's smart. It really is. But when you're talking about code that's working inside one computer in the same core memory that's meant to work together, it's too limiting. It's way too limiting. It's not the right model, and it forces us to do way too much work to accomplish the same thing. So, just to underscore, reading this history actually gave me a nice perspective on these things. And I think there's reasons why C++ was adopted, even after all the stuff I just said about how the compile time hierarchy stuff wasn't very good. One of the things that I didn't really appreciate was it kind of sounds to me like Strucev was really important in getting type checking for us. Like, C did not even type check function calls at the time that Strucev was making C with classes, right? And he recognized, because of his background in Simula, he's like, this is ridiculous. I think he gave an example like, if I do square root, like sqrt in C, parentheses 2, that doesn't work right now because it passes the integer 2, and it doesn't check that square root's taken a double or something, right? Or whatever it was taking in that particular version of the library he was using. He's like, that cannot be something that we have to catch at runtime, especially not in those days when debuggers are worse and everything is worse, right? Iteration time is slower. So you get this situation where you're like, I kind of see why these things took off. Some of these things, like the compile time, encapsulation hierarchies, they're coming in at the same time that C++ is making positive contributions that actually do help you program for real, right? And it's not like we can't think of uses for things like virtual function classes, like interfaces. Just that bare concept is a place where we still use those things today, even in new languages, those things. So there is that too if it's used responsibly, right? It's just that compile time hierarchy that was a problem. And this is a quote that I also want to include just to give Strucev credit. He's also on the same team. He wants the fast thing, right, to be easy for people to do. You don't want your definition of good code to be slow, right? So anyway, when you read through all this stuff, you're kind of rooting for everybody, to be completely honest. Even after all the suffering that C++ has caused me in my life, I was kind of like, oh, all right, I get it. I get it, man, I do. So that's the 35-year mistake. It's the distance between those 2 years. The year in which we could have had the entity component system, because the first person had sort of done something that was almost that, and the year in which we actually got the entity component system, which I'm not even saying is a good design or not. I don't even have an opinion on something like that, to be completely honest with you. But I think it was a really cool idea and an interesting architectural idea to explore. And so I'm really glad that we got there either way, but I wish we could have gotten there a little bit sooner. So unfortunately, the mistake, if that's 35 years, it does unfortunately not end there, because if you do a search on Google right now, and you're like, I need an OOP tutorial, I need an object-oriented programming tutorial, what will you see? Hit number 1 will have a domain model that has encapsulation that matches, you'll have a compile time hierarchy that matches the domain model exactly like we don't want. This person imagines, this is the number 1 hit. He imagines something called a special Iron Man that's slightly different from a regular Iron Man, because I guess in his mind, or whoever wrote it, I don't even know, it might be a team of people, there's some kind of a specialized Iron Man that I don't read comics, maybe that's a thing. Hit number 2, Java OOP, this is from W3 Schools. Again, not only is it a compile time hierarchy that matches the domain model, but it's one of the ones that you can actually find in those early papers. Stroop talks about vehicles sending cars, and if you remember, cars crossing a bridge that could be trucks or buses was in Simula day one. It's where they came up with that subclassing thing that they were going to do. So we're still pushing it today on hit number 2. Hit number 3 is 3 types of bicycle that come off a bicycle, right? And don't ask me why there's spaces in that and not in the mountain, but I mean, I don't even know. That's the top 3 hits. I stopped looking after that because I'm just like, I give up. So one thing that we could do to keep this mistake from propagating is just get this idea out there that compile-time hierarchies of encapsulation that match the domain model are not that good. Sometimes they work, like with distributed systems, or maybe microbiology, but a lot of times they're just more work than they're worth. And that would help. It would help a lot. And I would bolster that here at finally the end of the talk with this quote, which I think is the best one to end on. It's that the most treacherous metaphors are the ones that seem to work for a time because they can keep more powerful insights from bubbling up, right? We got this thing in place. There was this compile-time hierarchy that matched the domain model idea, and it was stopping all of our other architectural development because everyone was saying it was going to work and it was going to be great, and we just must be doing it wrong, right? But actually, that wasn't the case. And this is a hard quote to find. If you search for it, I'm not sure if you will find it, but if you read through, you will find it. It comes from Alan Kay. He's the one who said it, right? That's him sitting at his, I think that must be one of the original Palo Alto computers, right? The Alto, I think is what that one is, from Xerox PARC. So that's the actual end of my talk. Thanks, everyone, for listening. I'm surprised I was able to remember all of that stuff for this. You've been a wonderful audience. And I guess now Ryan Fleury will be coming up on stage to interview me and take questions from the audience. Is this correct? Sam?
What?
Sam, is that true?
I say it again.
The organizer, ladies and gentlemen. Please welcome to the stage Ryan Fleury, everyone.
Okay. Well, yeah, thank you for that talk. That was really good.
It was a lot of fun putting together.
Yeah. So, I guess the first comment that I would have is that it seems like I'm a little bit glad to see that people in the 60s, there's two things. I'm glad to see that people in the 60s were like using these techniques that seem to be re-emergent. It kind of makes it feel like there's like maybe like some degree of gaslighting since then. Like there's like all these, you rediscover these things, they seem to be useful. And then for some reason, like we haven't actually, that information has been lost, I guess. Do you find, I mean, I assume you find the same thing to be true.
Yeah, I mean, I guess the problem, so I don't even know if it's like gaslighting in that sense, right? Because it's like, I don't necessarily know, I didn't find a lot of evidence that people were like intentionally, obviously. Like it wasn't like somebody was like, I would rather promote my thing than this thing in Sketchpad that I noticed. That quote from Alan Kay is kind of instructive in this case. He honestly believed that having the thing be omniscient was bad. He's saying that this is bad, right? And you see the same thing from Stroop saying that this, switch, this basically switch on a type is bad. And so I think they just honestly believed that. They believed that these were bad for modularity, and in their minds, because they're so focused on the modularity, they were just saying this isn't good. And so it just kind of doesn't get propagated. This is the thing that you see all the time, right? If someone isn't good PR for their thing, it doesn't get propagated.
Yeah, that makes sense. So, in your own personal programming journey, you started with learning the traditional object-oriented sort of, or C++ templatization of compile time, hierarchies of encapsulation, and so on. I mean, I have an idea of where you changed or where you developed, but I'm curious about where you learned to not do that, and furthermore, from where you learned it, where did they learn not to do it? Did they learn from the original papers, or did the simple ideas just reemerge, or what is the story there?
So that's kind of interesting. So when I was younger, so when I started programming when I was very little, right, I didn't know any of the things. I wouldn't know anything about architecture. C++ wasn't even invented I don't think. Would it have been invented? So C with classes would have been, but C++ wasn't even like out in the world at the time when I would have started in like BASIC or something like that, right? So I definitely started without any of these notions. But then when I first went out into like, professional, I mean, my first job was hardly professional, but when I went out into the world of like commercial programming, I definitely like thought that everyone was presumably right about this. I just didn't know. And so I tried programming in this model and learned all those things because, it kind of has a Magic the Gathering feel to it. It's like you're learning a lot of intricacy, and it's just Magic the Gathering. It's something people made up that was fictional. But you don't know that. You think it's real, right? But you're getting into it in the same way you might get into Magic the Gathering. You're like, oh, I figured out that the template can do this thing. And it becomes its own little game, right? So I think it kind of went that way for me. And at the time, it was very obvious that this was stupid. Like if I'd actually thought about it, but I chalked it up to me just not knowing how to do it right, which I don't think was actually true. I think it was just like, no, these are actually just worse than what you were doing. Because what I noticed was things that would have taken me only a few days before were taking like months to like figure out all of the ways that I would have to do it in order to make it fit these things. And I think I was just too stupid to realize that probably just means it's just a bad approach, right?
Yeah, that makes sense.
So you had a second part of the question, which was, how did I undo it? That part is a little more concerning, I guess, because the only reason that happened was I happened to then program with people who had never done that. So there were people who never had the experience of being told to do this architecture or just ignored it and continued to program the old school way. And I was like, oh, these people are very successful and very important programmers. So maybe it's not the case that I just don't understand it. Maybe there's actually something to keeping doing this way. The reason that's more concerning to me is it's like, it means if those people aren't around, if they weren't around, maybe I would never have that experience, right? And so you kind of need this generational overlap of people who still remember the good things about the previous way to tell you that the new way kind of sucks, right?
And do you know, like, when you worked with those other programmers, were they informed by this older generation, like the 1960s papers of how they were doing these things? Did they just take those lessons, or
No, I think it's just a case of like if you were using programming resources from that era of even just the 1970s, you wouldn't be seeing, like, it was more academic, the places where OOP would have been talked about, right? Smalltalk was a thing that would have been in research stuff, right? And Simula was a thing with papers and stuff like that. But the person who learns to program, like, in the game industry and stuff like that, the person who learns to program on an Apple II is not being exposed to those things, right? So they just learned in an environment and using reference materials that did presumably kind of come through that culture, but it wasn't like they were, nobody was like, oh yeah, Doug T. Ross, man, and Plexes, like that's the stuff, right? It's like, no, like, so I think it's just more that they hadn't have had that idea pushed down on them in a way that they believed.
I had it in my head, but I got to check my notes here. So I think that I was curious about, I have a collection of like not exactly related questions or discussions. Like,
Hit me.
So one of the things, you introduced this subject by saying like, one of the arguments that people will use to promote like sort of object-oriented or I shouldn't say object-oriented, I should say compile time hierarchies.
If someone out there wants to come up with a catchy moniker for that, it is hard to say.
Right.
So we need something like OOP for that, right?
Yeah.
And it would be nice because, again, like I said, I think it's pretty important to draw that distinction because like Mock, who I quoted at the beginning of the thing, who did that entity-component system, he's thinking of it in terms of object-oriented. He's not thinking this is not object-oriented, right? So you can easily call yourself an object-oriented programmer and want object-oriented principles to apply to your code base and just not think about that compile time thing. And it seems to work pretty well.
Yeah, it kind of seemed like the object-oriented part of drawing boundaries, it's not, it might be descriptive of a system, but it's not prescribing like where to put those boundaries exactly.
Yes, exactly. And also, furthermore, it's something I think we could all agree about, right? I don't know that a hardcore object-oriented person, like certainly not Alan Kay probably, would never agree that making like an API boundary around something was that object-oriented if the thing was fairly large, although he might. But we can all agree that that's a thing we want to do. Like, I don't consider myself an object-oriented programmer, but I consider that to be a good thing to do, and I think that's certainly a point of commonality. And I think most object-oriented programmers would call that an object-oriented thing to do, even though it really predates that. You could just think of object-oriented programming. One of the principles is sort of crystallizing that idea into one of their core concepts, and I think that's a good core tenet to have, right? To do that at the appropriate size, that's where I tend to part ways. It's like what that size is.
So, on the large team subject, you were digging through all of these historical papers and records and everything. Did you actually find any research about what people actually do for large teams?
So, one of the things is I was focused on figuring out where these ideas came from. So I didn't go looking for where I don't want to call them excuses, it's too disparaging, but where the justifications came from, right? So what I can tell you, so I don't know, that'd be a whole nother talk. Right? This thing took 2 hours or something like that, right? So that's a whole nother question. It would be very interesting to answer. But what I can tell you is during the course of the development of these core ideas, I never once saw anyone talk about that. And they were always like one person doing a thing by themselves, or two people developing things by themselves. And to the extent that like larger teams would have been involved at all, it might have been on the Simula side. Like some of their opinions may have been influenced by, in ways that they didn't directly, like they didn't attribute any of those things to it, but maybe they were seeing people use Simula out in the world that had something to do with it. But I don't think there were that large teams working on Simula either. I don't know.
Yeah, it's kind of interesting alone that the history of computing, it's always large team or small teams pushing large improvements like successively. So it's interesting to optimize for large teams in that way. But
well, and you might even say it creates a bit of a problem because it means that like if the innovation happens in small teams, but we do need large teams of people to do certain things, it's like it's kind of hard to figure out where the innovation in that comes from, because if our only risk comes to these few people doing something, they're not having the same experience as a large team. So maybe it's like small teams doing something on the side of a big team is where we get some of that innovation. I don't know.
So I'm kind of curious about a few programming ideas that a lot of people use, like that you regularly use in your programming came up. One being like discriminated unions or tagged unions, as sort of like forming this like mutually exclusive branching structure, as opposed to like the fat struct model where it's like it's one unified type. I'm kind of interested to hear like what you think about like both of those things are you've said are like good in their respective situations. I'm curious about like when you know that introducing boundaries of mutual exclusion like in a discriminated type is useful, whereas the sort of large fat struct thing stops being useful in those cases.
So I don't really think of them as distinct. I think of them as sort of the same things. I'm just trying to use terms that other people think in to communicate that. So the way that I normally think about it is there are two types of situations I might find myself in. One is where the domain model itself, like literally the thing, is telling me clearly that these things are mutually exclusive. And that might be a place where I, have more in common with the OOP side of things. So I'm like, I see why you guys would think about if that was true about this thing. So in those cases, I would use a discriminated union because I prefer to write code in like a verb-oriented way, not an object-oriented way. But I'm just doing the flip side of what they're doing with their virtual function in those cases, right? I just think it works out better in my way, but that's just, that's my personal opinion. It also has to do with what type of system you're making, whether or not people are going to be adding types to the system more frequently, or whether they're going to be adding actions. I tend to find that people add actions more frequently. That's why I focus on that. But either way. So if I can see that this is by definition mutually exclusive, then I'm discriminated union. And the reason for that is the exact same reason for Strustrip and everybody else, to catch errors. I don't want to make that a fatty struct where I'm accidentally doing code that's going to do both things. So I try to basically replicate that Simula style thing, or really it's Tony Hoare's, right, Sir Tony Hoare's idea of that. I try to replicate that, and it's just unfortunately C++ doesn't really have good support for that. Like I said, standard variate's not very good in my opinion. The real thing that Tony Hoare wanted would have been great. So I would love that feature. The fatty struct qua fatty struct, and like I said, I mixed these two together, so I don't think it's that distinct to me, but the idea of like feature flags or something like that, right? Like I'm gonna hit this bit and then it means that this path might be taken. What the Plex guy, right, what Doug T. Ross would have called those like switches, right? That to me is for mix-in, as they call it, right? When I know I'm combining lots of things together, right? Like a tasty stew that's going to be delicious and it's going to taste fabulous when you use these entities, right? That's when I reach for that. And I think those are they're very simple. You can teach them to someone in an afternoon, and they can apply them pretty directly right away. And that's one of the reasons why I think they're so much better than things like the compile time hierarchies, where, I've seen programmers tie themselves in knots and spend months trying to do something that literally that approach would take them 30 minutes. Right? So.
And I'm a little confused about the exactly what. So Looking Glass, you introduced them as using like sort of the fast struct model, but it sounded like they ended up with an entity like component system thing where they split everything out into like they pulled out common parts of entities and isolated their storage. Did they make that transition, or did they use one early and then the second later?
Can I ask a question to the audience?
Yes.
Sam, how much time we got?
We still have time right now. Maybe, it depends. There are multiple paths that could be taken, and the split point is in about 25 minutes.
How badly do you want a complete version of that answer versus a summary answer? Because I can answer that very accurately.
Okay. Yeah, let's go with the
Dimensional
accurate one.
upload speed increased. Right. The dimensional shift now no longer cares how complex the components of the original part are, and will save each part as a single collection of
deleted
particles
scenes
that can be instanced easily.
to keep this talk somewhat under 2 hours, which hopefully we did, and now won't do.
I'm working on
So
it,
I'll
but are
skip
you
some of this
saying
just to
there
keep
is
it
another
relatively
layer?
quick.
Is it a sensor
So
limitation?
inside Ultima Underworld, an entity was basically
Helpful.
a fatty struct overlay. So the way that it worked is you had an entity, and then if there were two separate things like hit points and fuel that were generally mutually exclusive, meaning an entity probably can't have both of them because fuel is used only for like lanterns, and lanterns don't have hit points, then we'd put them in the same place, right? That was Ultima Underworld, right? And of course, this is rough because it's like it means that when you're accessing one of these, you're secretly also accessing the other, right? Because they're in the same place. And so you could have an error where you were doing something where like you're checking the fuel or you're checking the hit points. In this case, like you're checking the hit points, but you're secretly checking the fuel, and then you delete the entity, because that's what it was thinking, right? And this is Mock. His picture didn't make it in. I'm glad I get to show him now. He's the guy who did a lot of the implementation on the dark object system. He came on the scene in Ultima Underworld 2, and he's the one who coined that phrase, that quote I put up. That's him, the compile time hierarchy. He's the one who crystallized that, right? He comes on because in the earlier ones, like it was Doug Church and Dan Schmidt and a bunch of people who did Ultima Underworld 1. He comes on Underworld 2, and he actually literally had that bug, that fuel bug. He wrote a thing for damage where if you threw an empty lantern at a wall, it would enter the damage system because it was supposed to take damage from hitting the wall, and it would be like, how many hit points does the lantern have? It'd be like 0. It's like, well, I guess it's out of here. And so empty lanterns thrown at walls would just disappear, right? And so he had to fix that bug by doing exactly what you expect. He'd have to check. He'd have to manually add that code. And so, they didn't like this. Because remember, these guys, and again, much like, Ivan Sutherland and Doug Ross, these guys were super smart MIT people. And Sutherland was also Carnegie Mellon and Caltech, right? It's like kind of nuts going through the whole gauntlet there. The folks at Looking Glass are MIT graduates. They're super, super smart guys. They do all this amazing stuff. So they don't want to have this happen, right? They just don't know what else to do because they have these like really hardcore memory constraints. Yep. And furthermore, they talk a lot about the sort of trade-offs you have to make. So if you have a fuel system that needs to store stuff and you have a combat system that needs to store stuff and you do make space for them, it means that if you do, if you're using that overlap, it means that if you then decide you need an entity that has combat and fuel because we wanted to add that, it's like, crap, I've got this overlap, I can't do it, so now I have to make a trade-off. Like maybe I shrink the amount of data that the combat system can store, and that sucks, right? Because now I'm forced into this decision I didn't want to have to make, and that's just what the kind of situation they're working under, the kind of constraints they're working under. When they go to do System Shock, which is the RPG, so they do Ultima Underworld 1, 2, and they do System Shock. I'm just following their lineage. They have Terra Nova and Flight Unlimited, which I won't cover because they're not the same in terms of like lineage really for the teams and how they were doing RPGs. This is just the RPGs from Looking Glass. So it kind of looks like that. I'll skip this because it's not part of talk. They go to an outlinking kind of structure. So what they do is they say, all right, we kind of want something better than that. So what we're going to do is we'll have our entities. We have a little bit more memory to work with now. So we'll have the entities have their shared part up front that everyone roughly has. So it's kind of fatty, but not that fatty. And then everybody gets one pointer out to something. Right? And we'll try to make those things be things that don't have to combine together. But it's still a limitation, right? Because they can't have two of them, which they would have liked to have had. So that's how they got there. That's what System Shock was. It was like one outlink per entity that could extend it. And now that solves their growing problem, right? It's like we can just grow things arbitrarily, and they don't like overlap some unrelated system or something like that. But it doesn't really allow them to combine them in that way that they would have liked. So it's still almost the same limitation. It's just more of a memory optimization at this point, right? But it also catches this error, because now you sort of have a discriminated union going on, so you can't access fuel off the base entity because it doesn't have it, so you have to do something like this, where like if it's a light source, I can get the light source, or better yet, I can only return a light source pointer if it was a light source, and so then it's kind of more foolproof that I can just check one pointer and good to go, right? Again, I'm blowing through these, but yeah, this was me making fun of standard variant, yeah. So Flight Unlimited, I'm just going into this because it sets up the entity component system thing. Flight Unlimited actually had, it was the first thing to use C++ really heavily in the company. And so they were using new and delete like you're supposed to do in C++. And unfortunately, that totally fragmented memory, totally like thrashed out memory and fragmented memory. So I don't know if this is well known, but basically Flight Unlimited is a game where you like fly around, in a thing and whatever. It was a very popular flight sim at the time, actually. And you'll notice that in the cockpit here, there's gauges, but there's no fuel gauge. Right? There's no fuel gauge on there. It's other stuff. There's no fuel gauge at all. But sometimes it would say out of fuel. It would just be like out of fuel, right? And what out of fuel was actually the memory's too fragmented. So what it would do is it would say out of fuel. It had like an executable that was sort of running as sort of a batch restarter for the main executable. It would just close the whole rest of the executable. So it would save the game state, close the executable, reload the game state, and then you're back to good. This is Tom Leonard. So Thief the Dark project comes on the heels of this. This is Tom Leonard. He's actually the guy who, as far as anyone can remember, that I've been able to get a solid story about. He's the guy who actually comes up with the idea of sort of the entity component model switch. And I didn't really call it, again, too much stuff getting cut that we're going into now, so I guess 6 of one, half dozen of the other. But the idea of saying, okay, instead of entity.get hit points, we're going to say hit points.get entity. This is that's a big switch if you've never thought about it before, right? He's the one that, Mock says, I think it was Tom who came up with that. And the reason is so that the types line up. It's like now, instead of having either tons of functions like get a hit points thing, get a this that are on, an entity, which would suck, now we just ask the actual thing, the hit point system, and it's only going to return one type, which is like a hit points type to us, right? And so anyway, this is what they're thinking about when they make the entity component system, and it comes from all of those experiences that they've had. They want to avoid fragmentation because they just had to make a thing that restarts the game, right? Which was Flight Unlimited. They want arbitrary sized properties, right? Because they don't want to make those trade-offs between combat systems and fuel and whatever. They also had additional things, which is they wanted designers to be able to create types at runtime, so they kind of want bags of properties that they can have designers create. And they want designers to be able to do things like create domain model hierarchies in the editor because they're thinking in terms of the domain model, and it's just not implemented that way, right? So they do those things. And then finally, the how fast is the fastest case thing. That was from Doug Church. He was like, okay, if we're doing all this pie in the sky stuff, we have to figure out some way that it's still going to be as fast for physics compute and stuff as what we used to do. And so what he did there was he was basically forcing them to go, we have to consider some way that this is all going to work. And that was the system boundary drawings part. So that's the really fast part of this. And by the way, this is what it looks like inside the Dark object system. If you want to create a property type, right? It's, like I said, it's still OOP looking, right? Like you could pass this by an OOP person and they would be fine with it, I think. So it's again, not OOP, it's just not that hierarchy thing, right? Yeah. So there you go. I think that's everything.
All right. Let's see what else I've got. Yeah, so I guess one interesting thing about what you were saying is that what it has to do with the object-oriented the original object-oriented work came from these like distributed systems and everything. And I know you've talked a lot about in the past like Conway's law and how like introducing these boundaries, or it's not introducing these boundaries, it's the fact that when these boundaries arise, they cause friction or difficulty. And I guess, would you characterize this object-oriented thing as like creating those boundaries unnecessarily? So they didn't arise from the problem, and so they're causing difficulty in that way.
I would sort of say that. I guess the only like caveat I can think of there is, I think that the part where you said the problem the problem doesn't arise from it or whatever, or the it doesn't arise from the problem, I think is how you phrase it. I think a person who thinks in terms of object-oriented programming and is an aficionado of that would claim that it is arising from the problem because the domain model looks like this, right? And so I don't agree with that, but I don't know what they would agree with, right? And so from my perspective, I agree with you. These are things that just because as a human, you're going, I like to categorize things into groupings because that's something that we do, right, linguistically. It's all quantum physics at the end or something, right, bro? So it's like, these are arbitrary categories that we're drawing. There's no reason to think, just like I don't think the laws of the universe think of you as Ryan Fleury in a computational sense, but I think of you that way. It might not make sense for you to have the computational version of Ryan Fleury be about Ryan Fleury instead of just a collection of things that produces to the end user the effect of Ryan Fleury, right? So to me anyway, that's sort of the difference there, right? It's like I don't see the model inside the computer may have very little to do with the model experienced by the user, which again is in direct conflict with like what Alan Kay wanted to do. He wants, and again, you have to remember the mindset. He wants to do education. He wants to teach people about computing. He wants it to feel like you're programming in the same way that you see the real world. And in some ways, I think if we could just get to the point where, and maybe he does think about this now, I'm not sure, just get to the point where he thinks, oh, well, that's just when you use an application. That's what it feels like. It's not what it is under the hood. Then I think I'd be right there with him, right? So.
Interesting. All right, I'll check my list, and then maybe if anyone in the audience has questions, then I will ask. But I'll check my list first, since I'm up here talking about it. Okay. I had 2 pages. I did that one. Oh yeah, I guess another thing. So I guess some of these are like not exactly questions, but they're like, I formed a mental model given your talk, and I want to run it by you and see if it makes sense. So another thing that I guess is implied by introducing these boundaries between parts of your program when you could have not done that in the architecture, but you did for one reason or another. The interesting thing is that you were talking about is it Sketchpad? Yeah, Sketchpad. You have some layer which is like quote unquote omniscient, like it knows it has full context of what's actually happening. And in my mental model, I'm like, that's similar to when like an actual like civil engineer or something is like going and building a bridge. Like they're not like, how do I build a bridge without knowing what the landscape looks like, kind of thing. So it's like, so a lot of the design decisions in C++ or in all of the other paths that you iterated, it seems like they're about like removing context or trying to find the minimal set of context. But I assume like that doesn't seem helpful. I haven't found that to be helpful because of what you have taught, basically. But I'm curious.
I kind of feel like you're on your own orbit now, and you totally know exactly what it is,
okay.
Right? I mean, yeah. Honestly, you're one of the best system architects I've ever seen.
Oh.
Full disclosure,
Gee,
right?
Well, thanks.
Folks at home, seriously, like it's insane. So you don't need me to tell you what to do.
All right, well, thanks. I appreciate that. But so I guess I think that's probably it. I'm having to turn through these 2 pages here, but
well, to answer that question though, about the removing that context,
right?
I do think like that's part of why it's frustrating to maybe look at the history a little bit, because what it looks like to me from like the bird's eye view is like instead of asking how do we achieve code reuse and modularity while preserving our ability to solve the hardest problems, it looked more like it was like, let's just redefine the problem to be simpler and solve that. And to me, that was one of the big things about the Sketchpad thing as well, where it's like, okay, you had working examples of this that are pretty well documented. I mean, if I can go figure out most of it now, looking back, than at the time when you could have actually talked to Ivan Sutherland fresh off of the implementation when he remembered it all, right? Yeah. And so it does really feel like there's a failure to engage with the hardest problems. And I think one of my takeaways from it, which you're from reading the history, which is not, it didn't really change my mind about this, it just reinforced kind of like my feeling about it, which is, I think when you're designing new things, you should focus on the hardest stuff. Yeah. You should say, what solves the hardest problems? Because we can always then take that and scale it down and remove things from it or dumb it down for people to use in cases that aren't as hard. But it's almost impossible to take something that only solves simple problems and scale it up into something that solves hard ones. And so that's really the thing. And I don't blame anyone in this that I covered here for that at all, because the conditions they were working under are awful, right? I mean, they have none of the benefits we have today. They were working with computer systems they barely got time on half the time. It was hard to debug all that stuff, and they're having to invent all this stuff themselves, right? They have nothing to fall back on. So it's nobody's fault, but going forward, it's like, when we have good tools, let's attack the hardest problems, and that will be where we get our really good architectures. That's my feeling about it anyway.
Do you blame Y Combinator at all for like the internet?
I'm about to blame them when I see what they post about this talk, and somehow manage to miss all of the good arguments you might have about it and argue about something else, like whether or not that was the right use of discriminated union, which 100% will happen, right? And you're just like, guys, who cares? Like, that does not matter right now, right? But okay.
Yeah, because I think like actually programming, that tends to be one of the harder problems. Is I don't know. You've said it 100 times already in the talk, but where you draw those boundaries, because it's not that modularity stops being useful, it's that it's a wall you're introducing that makes something more difficult. And so if you put that right into the middle of the hard problem, like you say, yeah.
And I think that is the fundamental struggle. It's why architecture is so hard. And it's also why architecture is potentially difficult to reuse. Architecture, not like reuse inside an architecture. And it's because when you draw those encapsulation boundaries properly for a particular problem, you save orders of magnitude of work when you do it properly. And where you draw them could very well be different for different types of things you're trying to solve. And that makes it hard to say, okay, here's an architecture that just works across things. Or one of the reasons the compile time hierarchy thing I think is a bad idea is not just because I don't think it's very useful in general, but it's also because it's Procrustean. It's like this one-size-fits-all approach that I don't think really even fits that many problems, but it certainly doesn't fit all problems, right? And so teaching architecture, I think it would be better to focus on more flexible thinking and thinking about drawing the encapsulation boundaries with intent, not with a fixed model in mind. And if that intent leads you to a very unusual placement of the boundaries, as long as you can prove that it's actually getting you that leverage and not introducing cuts in places where it makes programming difficult, then you should do that. You should follow that sort of weird structure, because that is probably right.
Yeah, that makes sense. Okay, well, I think I've exhausted all the questions or discussion topics. Or they would be rehashing things that I wrote them down and then you covered them in the talk, and I was like, oh, okay. So I'll ask the audience, does anyone have...
Should we just cut now? Is that good time to stop?
Well, we can do one. We have maybe 5 minutes.
Okay, shoot, sorry everyone. Okay, Raphael, do you have a question? You can just speak out.
Yes.
If we had the solution in the 60s and we saw the power of Sketchpad and why was, let's call it Dark Loop, still able to gain foothold and catch on and suppress the good solution? Was it a succession of knowledge transfer problem, or was it just because Dark Loop is such a catnip for programmers because it's a lot of interesting problems? How do I represent that? Or was it something else? Or why did it catch on?
I mean, it's very speculative to try and guess something like that, obviously. I think you touched on some of the answer there, which is that I do think people want to divide things into hierarchical categories kind of naturally. I mean, we did that with the natural world when we were trying to do biological classifications long before we had really any basis to do so, like before we knew about, DNA or anything like that, or how, those things might have happened. So I think it's a natural thing for people to want to do to make those classifications. So there's some of that. And thinking that there's this easy sort of model that just goes from what you see. It's like WYSIWYG architecture. Like what I see in the real world is just what the code looks like, and we're done, right? So I do think there's a little bit of that, but I think the real story is just that history is very messy, and in order for something to gain traction, somebody has to champion it. Someone has to do the work of implementing it into a system and doing a good job of that, right? One of the reasons we got the sort of compile time hierarchy thing is because that's what Strustrup kind of took away from Simula. It's what he implemented first into a language that became very popular. And he wasn't trying to do anything nefarious, right? He wasn't trying to do anything dark. He's just like, I like this type checking thing. I used Simula, it was kind of cool. He did the work, right? I mean, you could say that about things that we see happening today as well. It's like, in order for something like, Rust or something to gain popularity, somebody has to build Rust first. Somebody has an idea of what it's going to be. Is that idea good or bad? Who knows? But in order for it to even get judged in the marketplace, someone has to do that. And the bottom line is, nobody who looked at Sketchpad was thinking in terms of architecture other than what I said, which is like virtual dispatch, basically. And, I didn't go into the talk, but Alan Kay was predisposed also to think about that virtual dispatch as being very important, because the other references that I didn't mention, but they were in that quote, I said we're not going to cover them. They're like the Burroughs 5000 series computers, and there's this Air Force, this guy who wrote a file system thing where you put the way that you use the files in the file system were subroutines that were stored in front of the files in the file system, so it's kind of like a virtual dispatch thing. The Burroughs 5000 system also had this kind of virtual dispatch where there were tables and things. And so for Alan Kay, who we didn't really cover in here, the other 3 hours of slides, they're all there, right? But what he actually was seeing was he was seeing commonality there. He was like, oh, the Burroughs 5000, that Air Force thing that I thought was cool, Simula and Sketchpad are all doing this dispatch table thing, and they're all making classes with these dispatches on them. And then he's thinking molecular biology and this messaging, you're going to respond to these messages. That's what these dispatches are. They're how you're responding to different messages. And he just goes down that path because he's thinking that that's the core thing, right? Because he's predisposed to see it because he's encountered this idea multiple times. And so he's predisposed, I think, to think that that's where the power of Sketchpad comes from. Because, let's face it, would we have recognized that power at all if we hadn't had all of this experience? And I just randomly kind of stumbled upon this, oh, wow, wait, okay. That's really kind of interesting. If I had never seen an ND component system before, would I ever even have thought of that? Probably not. Yeah. So I think it's really hard. It's a really big ask. It's a tremendous ask to ask someone who's inventing C++ or inventing Simula to somehow get all of that. It's just not plausible. It's not plausible. It's a hindsight thing, I think.
We have a question right here.
So it seems to me that the pattern is always the same. You kind of come from school. It was my pattern too, and it seems that it's yours, right? You learned a certain way, and in school everything is kind of tied to business stuff, right? So it's very easy to think about you have a client with an invoice with items, right? And usually it doesn't go that deep into very high hierarchies, but we kind of just learn that pattern, and then we just start using it. And you have a hammer that is a melee weapon, that is a weapon, and whatever, right? And then we have to have the luck of finding somebody on our path that kind of snaps us out of this and shows us a different path. But also, these people are kind of disappearing from the industry. So my question is how do we fix this problem? How can we improve this? Because it kind of feels like you're trying to get smokers from stop smoking long after they're smoking, you know what I mean? So
Well, I guess I would say you're at the right conference. I mean, that's a lot, right? I mean, I don't know. You start doing stuff like this, and you try to go through the history and show how it happened and stuff like that. And that's it. I mean, that's the best you can do is put these ideas out there, suffer the Hacker News thread that you will then have to endure, right, or whatever else has to happen, and then you hope that maybe some of those ideas get picked up and people think about it more critically. I think we're out of time, correct?
Yeah.
There is coffee. We're going on break now. We'll be back at 20 past for Dennis.
All right. Well,
I hope
Yes.
I will be in the audience, anxiously watching this talk. This is from Teardown, right?
I think so. Yep.
Okay. I'm excited to see this one. I'm really looking forward to it, Dennis. All right.
All right,
So
thank
we'll
you so
be back
much,
here at
Casey.
20. Thank you, Ryan.
Yep.
All right. How developers stop learning the rise of the expert beginner. We call these influencers. Oh, damn, look at this. I click one page and I'm back at the Turd Brown. We're back at Turd Brown. Let's go. Let's go, Turd Brown. All right. The rise, let's see. Beyond the Dead Sea, when good software groups go bad. Okay. I recently posted what turned out to be a pretty popular post called How to Keep Your Best Programmers, in which I described what most skilled programmers tend to want in a job and why they leave if they don't get it. Okay, I mean, that sounds like a great... I wonder if I align with that. Today, I'd like to make a post that works toward a focus on a software group at an organization rather than one on an individual journeys of developers as they move within or among organizations. This post became long enough as I was writing it that I felt I had to break it into at least 2 pieces. This is part 1. Okay. In the previous post I mentioned, I linked to Bruce Webster's Dead Sea Effect post, which describes a trend whereby the most talented developers tend to be the most marketable, and thus the ones most likely to leave for greener pastures when things go a little sour. On the other hand, the least talented developers are more likely to stay put, since they'll have a hard time convincing other companies to hire them. Damn. The Dead Sea Effect. I mean, that really is just I mean... You gotta feel at least a little bit bad about just calling a group of developers. You're like, yeah, that's the Dead Sea over there. You see those guys over there? Dead Sea, nothing living, can float a lawn chair on it. Absolutely buoyant, filled with salt, terrible. Is this me? 2X Gang, Junk Matter, my old enterprise company, gang. Yeah, this serves as an important perspective for understanding why it's common to find people with titles like super duper senior, senior principal fellow architect awesome dude who makes a lot of money and perhaps even wield a lot of authority, but aren't very good at what they do. I've worked in this. I've worked in that, and it was emotionally bruising. I just want to see somebody get on the keyboard and make something. Okay? For me, that's how I know you're a super duper principal fellow architect awesome dude, is that you can actually make something. But that perspective still focuses on the individual. It explains the group only if they assume that a bad group is the result of a number of these individuals happening to work in the same place, or possibly that conditions are so bad that they drive everyone except these people away. It's a beautiful drawing. It's a beautiful drawing right there. It's so smug. Such smug. Absolutely beautiful. I believe that there is a unique group dynamic that forms and causes the rot of software groups in a way that can't be explained by bad external decisions causing the talented developers to evaporate. Make no mistake, I believe that Bruce's Dead Sea Effect is both the catalyst for and the logical outcome of this dynamic, but I believe that some magic has to happen within the group to transmute external stupidities into internal and pervasive software group incompetence. So my personal experience with this isn't, I think I understand what's happening here, but my personal experience goes something along the lines of Technology X is really exciting. People feel very excited about Technology X. There's somebody there that's just a really slick talker that can really convince people of a position or a stance. They take Slick Talker X and they give him authority. He convinces everybody, gets the stakeholders and everything. Next thing you know, you're using new technology, whatever new technology is, and then you start building on top of it, and it causes such swirl and difficulty. And then eventually people start leaving. A good example of this really was, reactive streams? Did I get this right? I want to say I got this one correct. Maybe I'm wrong. Maybe it's not called reactive streams. Gosh, what was it called? It must not be called reactive streams. I was a contributor on it, so I know it's not. and I don't recognize any of these contributors, so it can't be that. In fact, it makes me think that there might have been some purging going on here. Anyways, gosh, what is it called? It had the word reactive in it for sure. But anyways, it was this idea that you could somehow model all of your applications like transformations and drive everything from the server with like a generalized protocol, which in some sense is not a bad idea. But the problem is that it fundamentally missteps one thing, which is that the server should just drive the app completely, as opposed to just having like the app have this super complicated front end in which is driven by this knowledge on the back end. And it just kept going, and I spent so much time on it, and so many people spend so much time on it. And then people stopped wanting to work. This was a Netflixism, by the way. And people just stopped wanting to work on it. And it's all because one person could convince everybody how important it is to have back pressure and reactivity and all the fancy words. So I've seen the Dead Sea effect. In the next post, let's see. In the next post in this series, I'm going to describe the mechanism by which some software groups tend toward dysfunction and professional toxicity. In this post, I'm going to set the stage by describing how individuals opt into permanent mediocrity and reap the rewards for doing so. Learning to bowl. Before I got to any of that, I'd like to retreat you with a history of my bowling game. Yes, I'm serious. I'm a fairly athletic person. Doubt. You can't just call yourself I'm pretty up. I got a touch of athleticism. Growing up, I was picked at least in the top third or so of any people for any sport or game that was being played. Damn, kids regaling us with the grade school antics right there, no matter what it was. I was a jack of all trades and a master of none. This inspired me in a sort of a mildly inappropriate feeling of entitlement to skill without a lot of effort. And so it went when I became a bowler. Most people who bowl put the thumb and two fingers in the ball and carefully cultivate tossing the ball. Okay, before he keeps on going, I already know where this is going. He only puts two fingers in and gives it some spin, baby. That's what I do, of course. I feel akin to this article so far right here. And carefully cultivate tossing the bowling ball in a pattern that causes the ball to start wide and hook into the middle. With no patience for learning, I discovered that I could do a pretty good job by faking it by putting no fingers and thumbs in the ball and kind of twisting my elbow and chucking the ball down the lane. Let's go bowling at our next terminal stop meetup, and the entire thing like losers. Let's do it. Palming a pink 8-pounder and throwing it. Dude, that's me. It wasn't pretty, but it worked. It actually worked pretty well the more I bowled. And when I started to play in an after-work league for fun, my average really started to shoot up. I wasn't the best in the league by any stretch. There were several bowlers, including my former manager of mine, who averaged between 170 and 200. But I rocketed past 130, 140, and all the way up to 160 range within a few months of playing. Not too shabby. But then a strange thing happened. I stopped improving. Right about 160, I topped out. I asked my old manager what I could do to get back on track with improvement, and he said something very interesting to me. Paraphrasing, he said something like this: there's nothing you can do to improve as long as you keep bowling like that. You've maxed out. If you want to get better, you're going to have to learn to bowl properly. You need a different ball, a different style of throwing it, and you need to put fingers in it like a big boy. I'm sure there's a "that's what she said" joke somewhere within this statement. And the worst part is that you're going to get way worse before you get better. And it will be a good bit of time before you get back and surpass your current average. Hey, let's go bowling. I resisted this for a while, but got bored. By the way, this is such a good piece of advice. There's like all these things you have to do. Like there's a bunch of naturally talented people that get good at specific, like very high touch activities. Bowling, I'd put it in a high touch activity, just like golf. Like golf is something that you just have to swing 10,000 times to be okay at golf. You have to swing another 10,000 times just to be mediocre at golf, right? To be great at golf, you have to swing like 10,000 times a year, every year for like the next 20 years. It's crazy how hard it is to be good at golf. And so it's like, I totally get this. Like you can go in there and have a bit of natural talent, but the moment you want to go from natural talent to great, you have to like conform, into a certain pattern of play. You gotta just put your fingers in it like a big boy. I resisted this for a while, but I got bored with my lack of improvement and stagnation, a personal trait of mine. I absolutely need to be working toward mastery or I go insane. Feel that. I feel that hard. I feel that. My little kids are playing in the shop, so I can hear them playing out there. Golf is a sport for old people. Golf is hard, and I resigned myself to the harder course. I bought a bowling ball, had it custom drilled, and started to bowl properly. Ironically, I left that job almost immediately after doing that, having bowled probably 8 times in the year since. But not only did he go over, not only did he get all the stuff all set up to be that, he then leaves the job, which by leaving the job also breaks up with the activity. That's pretty funny. I don't know what sieste la vie means, I suppose. When I do go, I never have to rent bowling shoes or sift through the alley balls for one that fit my fingers. Dayfris, Rapid Returns, and Arrested Development. In 1980, a couple of brothers with the last name of Dreyfus proposed a model of skill acquisition that had gone on to have a fair bit of influence on discussing about learning, process, and practice. Later on, it would go to a published book based on this paper, and that book would refine the model a bit to its current form, as shown on Wikipedia. The model lists 5 phases of skill acquisition: novice, advanced beginner, competent, proficient, expert. There's obviously a lot to it, since it takes an entire book to describe it, but the gist of the skill acquirers move from dogmatic following of the rules and lack of big picture to intuitive transcending of rules and complete understanding of the big picture. I like that. The hidden knowledge, right? Because there's all these things that you do, like everything that you do, especially in programming, because this is the whole, like, it depends. This is why that statement is so frustrating, because it depends is just highlighting the fact that there's not really a concrete answer ever to anything. And so people often use that as a measurement to make shitty decisions, because you can just say it depends. It depends is the ultimate Swiss Army knife of making great and terrible decisions at the exact same time, right? And so, like, I break rules with programming, and I know that I'm breaking rules with programming. And it's for good reason, and then I often live to regret it. Like, one easy rule I have in programming is just never use the keyword extends in a language that allows for the keyword extends. And every now and then I just feel like this is the time. This is the one time that I know that extends will work in my favor. And then I use it. And so far I've lived to regret it every single time. But I feel like I can transcend the rules. And I feel like there is a time where I'm going to use extends properly, and it's going to feel so good. It's just going to feel so good. I just know it. It's going to happen. Programming foo, public bar. Programming is about compromises. It is. Composition over inheritance. I know, but there's always that one time you want it to work. There's that one time where inheritance actually seems to make sense on paper. I feel this too much. I feel this phrase too much. All things being equal, one might assume that there is some sort of natural linear advancement through these phases, like earning belts in karate or money in a corporate world. But in reality, it doesn't shake out that way, due to both perception and attitude. At the moment one starts acquiring skills, one is completely incompetent, which triggers an initial period of frustration and being stymied. Ain't that a fact? I still remember trying to understand how a class works and the amount of time I spent trying to learn how to program. It honestly I felt stupid. I felt like I wasn't capable of learning how to. I honestly felt like I wasn't capable of learning how to program. By the way, this is the craziest statement I've ever read in my entire lifetime. This is something that nobody has ever said. I don't think I've ever seen anyone say this. Single inheritance is terrible. Multiple inheritance is amazing. I don't think I've ever seen someone say that unironically. Like, I've never seen someone be like, you know what's better than single inheritance? Multiple inheritance. I wish I could get multiple inheritances. So do I. While waiting for someone like an instructor to spoon-feed process steps to the acquirer, or else, as Dreyfus put it, they, like a baby, pick up the imitation and floundering. You know, so this is my big worry about AI. Is that AI, I think AI is going to create a generation of programmers that have learned helplessness. This dude is cooking a long time. I agree. And that's a huge internal worry of mine. And let me explain why. Is that the process of coming up with how you should solve a problem is problem solving in itself, and it's a very difficult skill to have. Your ability to see from point A to point C in a short period of time, and then not only see what you need to do, but take that and morph it into something that is an actual solution, and then turn it from your head into something that the computer can understand, is such a huge like requirement for any software engineer to get great. And so my big worry with AI is that it shortcuts that, because it allows you to bounce it off somebody that always is suggesting. You always allow yourself just to not really put in that critical thought. And I'm very worried about that. I'm a college student right now, and it's crazy how many peers seem helpless and can't problem solve. I do think that there's going to be a massive hole in the market coming up here soon. Typically, like Bob Martin talks about this, Robert Martin, Robert C. Martin, Uncle Bob, he talks about the whole, in every 5 years, the amount of software engineers doubles. And he cited this as this was something, I'm not sure if it actually has continued ad infinitum or if it will continue. Obviously, it can't keep continuing for so long. But you get the idea that every so many years, some amount of people stop and a larger amount of people join in because it's just a growing field still. So therefore, it's really easy. You know, it's probably slowed down. Let's just say that, you know, let's just say this. I think this is probably fair to say. I think it's probably fair to say that there is going to be some sort of C0 constant that are leaving and some sort of C1 that's joining, and C1 is probably going to be larger than C0. And so we're right now in a growing population, and that growing population in the next 5 years is going to become a pretty decent amount of the overall portion of software engineering, whatever that equals, right? They could be this huge chunk, and they're going to only grow up in a world in which they know AI as how they start the process of solving a problem. And this, for me, causes some pretty serious, I think, effects. Learned helplessness is such a big problem for more novice programmers already. I'm currently dealing with 2 recent hires. Both of them have an incredibly hard time without Copilot. They don't know how to use Stack Overflow to their advantage. If it's not something they can copy-paste, they deem the problem unsolvable. You know, like, I do get it. I do think there is something very magical to the process of saying, I want to build something and just hacking your way to a solution. I think there's something very, very good. Brian, tell me how to fix my learned helplessness. Dr. Drero, you gotta go ahead. Dr. Drero, you're now on the big board. Go ahead, please. Tell us how. Why is that? Why is AI the same thing as Google in the early 2000s? Fix it by putting your fingers in it like a big boy. Hey, this is a Christian stream, sir. Come on. People in the past also thought Googling will replace knowledge source. AI can't do it so as much. People in the past did not think it so at all in any sort of level as AI. I mean, that's such a silly thing. And Googling did change. I just don't think that's the case. Yeah, they did not think that. Source, I was there as well. I don't remember any of these things. Google was looked at as a way to find information faster, and that is it. Yeah. Well, yes, I mean, the whole AGI thing, it doesn't make sense. Doesn't it depend on how you use your AI tool? I still think everybody needs to take a moment and see if you have the Copilot pause. Disable Copilot, start writing code, and watch your own brain shut down, right? Watch your brain shut down and watch yourself not use your own brain, but wait on something to tell you. You generally know what you want, and so you wait. I had a strong Copilot pause, right? I had a strong one. Copilot is basically spoon feeding. It's a real thing. You like stop engaging your brain. Joke's on you. I turned off Copilot a couple hours after. Yeah, it kept pissing me off. Yeah, most of chat has regular brain lag. They don't need Copilot for that. Damn, TJ. Anyways, I mean, I loved Copilot. Don't get me wrong. I still remember the magic of it. I actually want to create a main channel video for this because I feel so passionate about this. Because I do think that there's a lot of promise. I don't know. Anyways, we can pick back up. I'm worried about the learned helplessness. After a relatively short phase of being a complete initiate, however, one reaches a point where the skill acquisition becomes possible as a solo activity via practice. And renewed and invigorated acquirer begins to improve quite rapidly as he or she picks up low-hanging fruit. I think this should be step 1. I don't see how this is not step 1 of program. This is my step 1. When I just said I want to learn how to program, the first thing I thought about was I want to be able to build a game. And so it's like the step 1 was me getting Java applets to run in the browser. Step 2 was learning about double buffers and making up my own physics. Step 3 was actually making a small little game. Like, I don't see how this isn't step 1 of any programmer, right? Because that's the point of programming. Like, that's what I worry. So that's the whole like learned helplessness / you feel like you can only imitate. You feel like you can't find answers. You feel like all these things is because you don't have this like drive to solve the thing. Option paralysis probably. Yeah, no, but again, that's like this problem with this drive. Like option paralysis should not exist. You should just pick anything, pick something, right? How do you just stop from copy pasting the solutions to write your own version of the game? Because there was no solutions. I wanted to write things myself. Right? I want to write things myself. Once all that fruit is picked, however, the unsustainably rapid pace of improvement levels off somewhat, and further proficiency becomes relatively difficult from there forward. I've created a graph depicting this, in which actually took me an embarrassing long time because I messed around with plotting a variant of the logistic 1/1 minus x function instead of just drawing a line in paint like a normal human being. You could have just done an inverse tangent, baby. All right, look at that bad boy. All right, this is real. This time, the exact path. Okay, so someone just asked, how do I avoid just copy and pasting the solution? Right now, if you look at the Doom game, the Doom thing that we're building, I'm building out all the stuff. I'm building out our own quad trees, right? Here, our own quad trees, our own iterators, our own stride, our own everything. And why am I doing this all? I'm doing it because I wanted to do it, okay? So sure, I'm sure what we could have done is just use some sweet compression library off the shelf, thrown it into Wasm, compiled it, and called it a day. But something about that just doesn't feel cool. You know what feels cool? Going, you know what I want to do? I want to build my own Huffman. I want to be able to try to test out a couple ideas I have. I want to be able to do some stuff with quad trees and how to make data even smaller. I want to be able to go through everything and do that. I want to invent the wheel one more time because I like that experience. I want to learn what's underneath the hood. I want the experience of becoming good at it. So it's just so why the I think the general problem is this is kind of a cultural problem, and I think this, you can see it in how people play video games. Some people play a video game to simply beat the video game. They want to go as fast as they can from point A to point B. But beating a video game isn't necessarily the point of a video game. Not always, right? Like in the lower ones, like in Mario and stuff, that was the point. Beating the video game was the whole thing. But in these less linear ones, it's about the game itself. Like you get to go and find the things in the game. You get to like experience the game. Like that's the point, is to experience the game and eventually get to the end, right? You show up at the end looking just freaking jacked because you went around and you did all the side things, right? Zelda mentioned, exactly. The point is to enjoy the experience. And I feel like people just, they have this notion of just getting things as fast as possible and finishing every last quest quickly as possible and get to the end, do as little as, boom, move on. It's just like, that's not really the point in life. Life isn't to move as fast as possible. Life is to pick up each one of those little bits along the way. There's a lot more. There's a lot more to a game. It's not a job. It's just a hobby. Yeah, treat it like a hobby. The point of a hobby is to enjoy the activity itself, right? In this example of what for, let's see. This is an example of what, for the purposes of this post, I call arrested development. I understand the overlap with the loaded psychology term, but forget the definition on purpose here. Please. In a sense of skill acquisition, one generally realizes arrested development and remains in a static skill state due to one or two reasons: maxing out on aptitude or some kind of willingness to cease meaningful improvement. For the remainder of this post in series, let's discard the first possibility, since most professional programmers wouldn't max out at or before bare minimum competence, yes, and consider an interesting specific instance of the second, voluntarily ceasing to improve because of the belief that expert status has been reached and thus further improvement is not possible. Interesting. This opting into the indefinite mediocrity is an entry into the oblique phase in skill acquisition that I call the expert beginner. Well, this diagram is entirely too large. Okay. Expert, let's see. Novice, advanced beginner, expert beginner. Competent, proficient, expert. Oh, interesting. Okay, little side quest that you never quite got out of. Wait, where were we? The expert beginner. When you consider the Dreyfus model, you'll notice that there is a trend over time from being heavily rules-oriented and having no understanding of the big picture to being extremely intuitive and fully grasping the big picture. The advanced beginner stage is the last one in which the skill acquirer has no understanding of the big picture. As such, it's the last phase in which the acquirer might confuse himself with an expert. A competent has too much of a handle on the big picture to confuse himself with the expert. He knows what he doesn't know. Is that ever true in programming? the cul-de-sac of learning, the cul-de-sac of stupidity. This is true during the advanced beginner phase, since advanced beginners are on the unskilled end of the Dunning-Kruger effect and tend to epitomize the notion that if I don't understand it, it must be easy. As such, advanced beginners can break one of two ways. They can move on to competent and start to grasp the big picture and their place in it, or they can graduate to expert beginner by assuming that they have graduated to expert. You know what the funny part is that I fall under this category right here. Am I the advanced beginner or the expert beginner? What I mean by that is that I've programmed long enough, and I've said this phrase many times, that all problems just come down to, for loops, if statements, and variable declarations. And so it's like, yeah, I don't understand it. I don't think it's hard, though. It just takes time. Like, so any problem is overcomable. It's just a factor of how much time and effort I want to put into it. That's how I look at that, how I look at it. So does that make me an expert beginner, or does that make me competent? I have tennis elbow. Okay, thank you. Wired. 10 years of experience. I feel the same. Yeah, it's just like I've seen enough problems. Way past competent, maybe. I hope so. But it's just like you see things where, like, if you've done something enough times, you realize that it's all really the same thing over and over again. Let's see. I don't think it's hard. It does not equal I think it's easy. I think they're easy. Everything. I don't think it's hard. I don't think things are hard. I think they're just time consuming. Right? It's just you have to do, because there's not, like, let's put it this way. There's nothing hard about, like, even in differential equations in Laplace transforms, even though it'd be 3 pages of just writing, they weren't hard. They were only hard if you didn't have the foundation before that. And so it's like, there's nothing hard about it. It's just time consuming. It's just like you have to go, okay, I have to, before I learn Laplace transforms, I first need to, like, go down this whole list of things you need to do. And then finally, when you're through algebra, you're through basic calculus, you're through more advanced calculus, you're now into differential equations, you're like, oh, this actually isn't that hard because I already have all the pre-knowledge. It's pretty straightforward now. It just takes time to understand it. Yeah, that's just how I look at it. It's just like, I don't know, it just seems easy. It's just a matter of, it's just a function of time. Time, motivation, yeah. Except P versus NP. I never got to Laplace. Laplace is pretty fun. In fact, Laplace was my favorite part about differential equations. This actually isn't an immediately ridiculous as it sounds. Let's go back to my erstwhile bowling career and consider what might have happened if what might have happened had I been the only or best bowler in the alley. I would have started out doing poorly and then quickly picked up low-hanging fruit of skill acquisition to rapidly advance. Dunning-Kruger notwithstanding, I might have rationally concluded that I had a pretty good aptitude for bowling as my skill level grew quickly. And I might also have concluded somewhat rationally, if rather arrogantly, that my leveling off indicated that I have reached the pinnacle of bowling skill. After all, I don't see anyone around me that's better than me, and there must be some point of mastery, so I guess I'm there. Fair. IQ is irrelevant. Yeah, I do agree. I do completely agree with this one. That works if your IQ is high enough. I think that most people's IQ is high enough. First off, IQ is a very faulty and goofy measurement. There's few people that have true learning disabilities that actually prevent them from being able to do things. You're probably not that guy. Honestly, you're probably not that guy. You're probably not the one with a learning disability. So don't worry. That's not you. Second, it's probably going to come much more down to you desiring to learn and putting in the full ass effort than it is going to be coming down to you physically being incapable of learning. Some coding guy, how you doing? Now, some people are just simply smarter and they're so good at it. And it's just like, I mean, some coding guy is a great example of this. He is just super duper smart. Okay? He's just painfully smart. And there's nothing you can do about it. Stop. No, guy, you are genuinely a smart guy. Okay, guy, we worked together for many years. Okay, I know. There's things I know. Okay, called out. You're a smart guy. No, you genuinely are a smart guy. I, like everybody else, have an IQ slightly above average. Precisely. The man understands averages now. Bruv, I beat the S&P 500 with a Tidal River. Yeah, so there you go. Some coding guy. You've just won. See, he's a smart guy. No, you are a smart guy. No, you are a smart guy. No, you hang out. Smart ass does not equal smart guy. You got it. Why is some coding guy doesn't stream anymore? He retired. I would call that more luck than smart, though. Yeah, I mean, fair. I mean, if you just invested in NVIDIA, you won. My IQ is pretty decent. I would say that don't ever worry about it. I think you would know if you have a true learning disability. It's probably not you. You probably, as someone who's learned how to program, you're probably capable enough to learn anything, okay? You probably have absolutely no hurdles in the way. I mean, you may have some, like I have dyslexia. I find reading to be a very difficult activity, and I can feel it. I can feel a momentum of frustration building in and out of my brain as I read. That doesn't mean that I use it as a crutch. It just means that I have to try. It just means I have to try harder. You know what I mean? The real shame of this is that a couple of inferences that aren't entirely rational lead me to the false feeling of achievement and then spur me on to opt out of further improvement. I go from optimistic self-assessment to logical fallacy as my bowling career continues. I know that I'm doing it right because as an expert, I'm pretty much doing everything right by definition. Your logical fallacy buffs, a circular reasoning begging the question. By the way, I love this line of questioning right here, of thinking about, like, it's one of the dangers of being, it's one of the dangers of being in a
Welcome to the Project Assembly Pioneer Progress presentation. Congratulations, the Phase 2 project part shipment is now ready for delivery. On delivery, Phase 2 will be completed and the construction dock will be constructed. After completion of Phase 2, the technologies of Tiers 5 and 6 will become available in the hub. These might feel intimidating after your previous experience, but rest assured that you would not be here if you were entirely incompetent. Highlights are oil production, railway transportation, the jetpack, and many more. Completing Phase 3 of Project Assembly is your next main objective. Just remember to focus on producing and delivering the project parts, and Fixit's faith in you will be strengthened. Phase 2 of Project Assembly completed. You have been performing more adequately under pressure and are closer than ever to saving the day. Perhaps you were the right choice for the job. Time will tell. You will now enter Phase 3 of Project Assembly. Continue as you are, and there should be no issue. For humanity. For Fixit.